Okay. You can start now, or because it's missing 2 minutes. Okay.
Just let's check if Professor Cerelleiras is with us. Okay.
And Andrea Solotar also. Okay, it's here.
Okay. We did co-host to Professor Cerelleiras. Professor Andrea Solotar is with us also. I will make her, I will make
Okay.
you co-host also.
Okay, good.
Professor Solota, co-host. Professor Solotar is with us. Professor Cerelleiras is with us. 1 minute to start, okay?
Okay.
Hello, how are you?
Hello.
I have a file that I would like to share for my presentation. I hope it will be okay.
Okay.
It will be okay.
Thank you.
Thank you.
Okay.
Okay. It's 2:15 now. So we will start right now. Good morning, good afternoon, good evening, everyone. It's my great pleasure to welcome you all to the ISAAC-ICMAM Conference of Women in Mathematics 2024. I am Karina Navarro Gonzalez, and I am honored to serve as the chair of this conference. On behalf of the International Community of Mathematicians from Latin America, ICMAM Latin America, I extend a warm welcome to all of you. We are thrilled to have you join us for this virtual first edition of the ISAAC-ICMAM Conference of Women in Mathematics 2024. ICMAM Latin America was born in 2020 with the aim of fostering vibrant community of mathematicians across the globe. In just a few short years, our community has grown exponentially, connecting researchers from all corners of the world. We are incredibly grateful to the International Society for Analysis, its Applications and Computations, ISAAC, and especially its president, the Professor Uwe Kaller, for all the support provided to ICMAM Latin America. We extend our gratitude to our sponsors, the International Mathematical Union, IMU, the Global Minds Project of the Ghent Analysis and PD Center in Belgium, and the Universidad del Valle, Cali, Colombia. Their contributions have been instrumental in making this conference possible. One of our primary goals at ICMAM Latin America is to build bridges between Latin American mathematicians and their international peers. We believe that fostering collaborations and exchange of ideas is essential for the advancing the field of mathematics. Moreover, we recognize the importance of diversity and inclusion in mathematics. It's crucial that we create an environment where everyone feels welcome and valued, regardless of their gender, race, ethnicity, or background. We acknowledge the challenge that women face in mathematics by providing a platform for women mathematicians to share their research and experiences. We hope to inspire the next generations of female mathematicians. This international conference aims to promote collaboration between the Latin American mathematical community and renowned women mathematicians from around the world. It is our hope that this conference will serve as a catalyst for new ideas, collaborations, and discoveries. Over the 3 days, we will be treated to rich program of talk and poster presentations. I encourage all of you to engage actively with the lecture, explore the posters, and seize the opportunity to connect with fellow researchers. This conference is not just about sharing our work. It's about creating a space for us to inspire, learn from, build meaningful connections, and share ideas. Together, we can break down barriers and build a more inclusive mathematical community.
Thank you very much for those inspiring words. And allow me to echo those sentiments as we officially open the ISAAC-ICMAM Conference of Women in Mathematics 2024. I am Andrea Hurtado, board member of ICMAM Latin America, and it is an immense privilege to see today the opening of the first version of this conference in partnership with the International Society for Analysis, its Applications and Computations, ISAAC. We, ICMAM Latin America, are truly happy to have built a close bridge with ISAAC and be offering you today a conference focused on empowering women in mathematics, building bridges and breaking barriers. We are incredibly fortunate to have an outstanding lineup of speakers consisting of Claudia Gareto, Thais Jordao, Carmen Judith Vanegas, Paula Cerejeras, Laura Miller, Jacqueline Godoy Mesquita, Maria Gordina, Luz Roncal, Rajula Srivastava, Irene Tubikanek, and Zoara Núñez Ramos, and our group of posters exhibitors from around the world. Their willingness to join us here at ICMAM is a testament to the quality and the importance of this event, and we are excited to hear their insights and learn from their groundbreaking research. As we go on this exciting week of talks and posters, I would also like to highlight the role that female young researchers will play in shaping the future of mathematics. ICMAM has always placed a strong emphasis on supporting early career researchers, providing them with a platform to connect with senior mathematicians. We are proud to offer this opportunity. Finally, I would like to extend our sincere thanks to everyone who has made this event possible, the organizing committee, our scientific committee, and all of the institutions involved. A special mention goes to us, our sponsors, whose continued support has been crucial to the success of ICMAM. And of course, thank you to you all, the participants, for being here and for your contributions to the mathematical community. With that, I am thrilled to declare the ISAAC-ICMAM Conference of Women in Mathematics 2024 officially open. I hope these 3 days will be an enriching and inspiring experience for all of us, and that together we will continue to push the boundaries of women in the mathematical world. Now, it is with great pleasure that I introduce Professor Paula Cerejeras, representing the International Society for Analysis, its Applications and Computations, ISAAC.
Thank you very much. Can you hear me?
Yes, Professor,
Yes.
I hear you.
It's an honor to be here in this in the first of this successful series of conference organized by the ICMAM. It's visible that this ICMAM organization of Latin America, who has started from 2020, has put a focus in the quality of the mathematics and young people to attend. So the plenary speakers are chosen since the very sessions from the high level, from the United States, from Europe, Germany, Italy, and so on. And it's quite nice to see the interest of the young mathematicians from Latin America to attend this conference. So I'm looking forward to this session aimed at women in mathematics, which I hope will be following the same lines of the previous. So I'm not a person for long speeches, so it's a pleasure to be here, and I hope for the best. Thank you.
Thank you very much for your words, Professor Cerejeiras. To finish this ceremony, we are very happy to have with us Professor Andrea Solotar, President of the Commission for Developing Countries of the International Mathematical Union, IMU, who will give us a few words. Please go ahead, Professor.
Thank you. Thank you very much. I am very happy to be here. I think that the work you are doing is really, really important. Being a woman who works in mathematics in Latin America, I know that there are difficulties that we have to face, and that it is not easy to develop our careers. Okay, so let me share a short presentation. Just a moment, please. Yeah, here. Okay. Okay, so here it is. It's about my work as president in the Commission for Developing Countries. In this commission, we know that, well, there are a lot of things to be done for the development of mathematics in developing countries, but moreover for underrepresented groups. Okay, so we take this into account, and we have been taking it into account for at least for the last years. So let me remind you that the main aims of this commission is to manage initiatives of the International Mathematical Union supporting mathematics in economically disadvantaged countries. Okay, so we want to promote the programs of the IMU for these countries. And even within these countries, we also aim to provide some special support to underrepresented groups, as I was saying. So, for example, when we have many programs, and when we, for example, talking about the grant selection committee for the grants for conferences, we pay special attention to how these minorities are represented amongst the group that we are going to help to fund. Okay, and of course for this we have to search for money, which is not always easy. And we have partnerships with some other organizations, just to mention a few of them. SIMPA, who also have this criteria, the Commission for Developing Countries of the European Mathematical Societies. Also, Malga is doing a great job in this. Okay, so you know that one of the first tasks of each elected commission is to fix a criterion of what is considered a developing country. Okay, and I can tell you that I have been studying this problem a lot, and it is because, you know, we use data from the World Bank, okay, concerning the gross national income of each country. But we know that it is not the only criterion for judging if a community, a mathematical community, needs help or not. Okay, but the problem is that it is very difficult to get data about some particular subject from all countries, and something we can trust on. Okay, so finally we are using this economical criterion, and we divide the countries in groups that we call priorities. So the current one is those for low income. Well, it's for gross national income per inhabitant, very small. This is our priority one. In Latin America, we have almost no country in priority one. maybe, yeah, I think in the Caribbean. Then lower middle income. Here you can see the numbers, the figures, and this is priority 2. We have some countries in priority 2. And upper middle income, which are priorities 3, 4, and 5. And then we have a new category this time that is for countries with a higher gross national income per inhabitant, but where research is not receiving enough funding from the corresponding government, okay? So in previous periods, we had 2 countries in Latin America, Uruguay and Chile, who were not considered as developing countries because of figures. But now, of course, we can fund some activities in these countries with one condition is that they are also participants from the other Latin American countries, okay? And the priorities are useful for different purposes. Okay, so now this is the composition of the current CDC. So you see that besides the President, Secretary for Policy, Secretary for Grants, there is 1 member, 1 elected member for each region, and then 3 members directly named by the Executive Committee of IMU. And then let me go a little bit to funding opportunities. We have travel grants, individual travel grants, and then we have this ABEL Visiting Scholar Program, and it gives money for visits of up to 1 month, is up to $5,000. And there is a condition that we don't like very much, and it is that the applicant should be under 35 years at the day of the deadline. And we have discussed this with them a lot of times because especially for women, it is low, especially for women with children. Well, even if it is an organizations, Norwegian organizations, they do not want to change the limit for women. This is something that I do not understand, but it is like it is. But the good thing is that we have another program that is, this is one with new funding this year, which is the IMU Simons Research Fellowship Program for developing countries. And here, the program supports travel costs for research visits from 1 month to 3 months. The person can stay longer. And it covers up to $15,000 for 3 months. But the good news about, well, it is for also for mathematicians in developing countries, but the good news is that starting from this year, it includes childcare expenditures in the budget you have to submit. And this is very important for us women in particular. So we have to be very careful because as soon as this opportunity appeared, we received some applications from mathematicians that saying, well, I will come with my wife and my wife will take care of the children and then I will need support for them. But this is not our target. Our target is mathematicians traveling alone with a child or children and needing some help with daycare, for example, while they work, okay? So I want to promote this program because in particular for women mathematicians, I think it is very important, a very important opportunity. Okay, then this program is not working at this moment, but then we have the conference support program. And in the conference support program, well, we have some money coming from different sources, but there, even if it's not written, we take care, the committee, the grant selection committee takes care of the fact that, as I was saying, minorities are represented, are well represented among the speakers and among the participants, okay? So, Okay, so this is eligibility criteria. And then we have a program which is called Volunteer Lecturer Program that is for visits for people going to teach in some developing country. And this is, I will be fast with this. But then I want to promote some scholarships that there are two programs, one called GRAID. And GRAID is for only priority 1 or 2, but it is for a team. For example, a team having a student in a developing country and with links to an international partner. And well, it is funded by donations. And we are very happy because there are lots of successful cases from people funded by GRADE. And then there is another program, which is called the IMU Breakout Fellowship Program. This is for all priorities for all the developing countries. And it is more money for funding a PhD, for example, during 4 years. And I really want to advertise this program because we have very few applications from Latin America, and even less applications from women in Latin America. So take into account that these programs exist and that we take care of, again, try to help women to develop a career, okay? So just to end my presentation, well, you know that we will have the next ICM in 2026 in the United States, in Philadelphia. Well, the travel support program has already closed applications on November 20th, if I'm not wrong. And we are going to hold some activities during the ICM, and I want to invite you all to participate in these activities if you will be there, because we will try to talk about our programs and to disseminate information about, especially about these programs for PhD and for master students, because we want to get participants from many countries that are not participating now. So you are all invited to take part in our activities. And thank you again for organizing this conference that is so important. So I will stop sharing. Thank you very much.
Thank you very
Of
much.
course, if there is any question, you can either send me an email or contact me in any other way.
Yeah.
Thank you.
We can find this information on the IMO website, right?
Exactly. Yes.
Mhm.
Yes.
Okay.
Mhm.
Well, thank you so much for this important information. Really, really. Okay. So our first talk will start in 20 minutes with the Professor Paula Cerejeiras at 2 p.m. Central European Time or 8 a.m. Colombian time. So see you soon.
En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua, y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso.
Okay. Mhm. We are back. Let me check. Okay. We have Paula Cerejeras here with us. It's a pleasure for me introduce the Professor Paula Cerejeras. The Professor Paula Cerejeras is an associate professor at the Department of Mathematics at the University of Aveiro. And a member of the CIDA Center for Research and Development in Mathematics and Applications. With over 30 years of experience in hypercomplex analysis, she has made significant contributions to Clifford analysis, radon transform, integral geometry, harmonic analysis, and inverse problems. Currently, she is a board member of ISAAC, the International Society for Analysis is Application and Computation. So today, she is going to talk about Q-rational functions, a new concept, and she will also share with us the motivation she finds within herself every day to dedicate energy and her time to mathematical activity, research, construction of theories, building theorems, etc. So please, Professor Paula, go ahead.
Yes. So before I start to project my slides, I will have to say that, well, you asked me to speak about my motivation for starting. Well, my interest in mathematics came very early in my age. Actually, mathematics or arts. But as always, we all have our role models, and the role models we choose are based on, well, our admiration for the person, their ethics in work, and so forth. In this case, funny enough, it was my father, but it doesn't matter who the persons are. It matters that you admire their personality, their interest in life, and so on. In this case, funny enough, he also didn't want me to follow for mathematics. On the other hand, the problem with role models is exactly that one. They are role models, but at one point or another, you have to choose your own line and your own path. And that was the funny part with me. My path simply was mathematics. One word of advice for all of you: it doesn't really matter who your role model is, but it matters that you are passionate for what you do and you feel that your life will be incomplete without that. And for me, my life would be extremely incomplete without mathematics. So, this being said, let me start projecting my slides. Wait, where was it? Full screen mode. And so let me share. Can I have possibility? I'm not allowed to share. Is it possible that you allow me to share the slides?
Yeah, let me see. You are co-host. Yeah,
Okay.
I think you can.
Oh. No, it's still doesn't let me.
No, let me check again.
Wait.
In the green button at the, yeah,
Yes, I have,
there are
but
button share down or
simply doesn't. Whiteboard, notes. No. Okay, that is funny. I don't even have access to the
yeah,
can share
because
at the
you are
time.
co-host now.
Just give me 5 seconds.
Mhm. Okay, we will wait some minutes. Or Professor Paula, maybe could you please send me your presentation and I can share for you?
Solved. It was a matter of permissions I had to install. Okay, let me view. Where is here, full screen, and
Okay.
you can see it now.
Yeah, yeah. Thank you.
Let me only check something else. Yes, everything is almost on. So wait is well, not the best, but it's going to work like that. So sorry for all the delays. My talk will be on Q-rational functions. And this is a joint work with Daniel Alpide in the US, Hugh Kaler from Aveiro, and P. Schneider, which works in Czech Republic, in Otia. So I will start with a short revision on classic reproducing kernel Hilbert spaces, from which the Hardy space is one of the best examples. You pick a function defined in the unit space, in the unit disk, and you use the reproducing kernel associated to the standard functions. And this has several applications in operator theory, linear systems, and especially in Shor analysis. Shor analysis is, let's just say, an analysis that you do in terms of Hilbert space and contractivity of the operators. So this Hardy space is simply characterized by the backward shift and the multiplicative operator. This is always unique up. This characterization is unique up to a positive multiplicative factor, but it describes uniquely the Hardy space. And this backward shift is described very easily by the quotient between F0 minus its evaluation at 0 pi and divided by z. The multiplicative operator works exactly in the opposite way by multiplying by z the function. So you can calculate the dual of this backward shift, and it's exactly the multiplicative operator if you're in the Hardy space, and it satisfies several properties. The commutator between R0 and the multiplicative operator is the identity minus R0, the dual of the backshift and itself, and this is simply considered as the dual of C times C, where C is exactly the evaluation of the function at the zero level. So this has applications in quantum mechanics for calculating the lower and the raising operators, but that is more visible when you pass for the Fock space. The Fock space uses as reproducing kernel the exponential one, the exponential function, and is described as the set of all entire functions, not only on the unit disk, but now in the complex plane, such that 1 over pi integral of model of z squared with a weighted measure is now finite. The interesting point is that this continuous measure can be linked to a discrete measure, a measure in the small L2 space, also weighted by the factor n factorial. And this makes a relation between, actually there is a squared missing here, but makes a relation between the continuous norm on the Fock space and the norm on the discrete L2 space, weighted discrete L2 space. Again, this Fock space is unique up to a constant, only that the multiplicative operator remains dual, but now of the complex derivative. And when you make the complex derivative, the commutator of the complex derivative with the multiplicative, now you get back the integral, the integration operator. Now this integration operator is seen as the dual of the backward shift. It's simply the integration on the path link is 0 to z of a certain function, and here z should be another variable. Now, the Q calculus, you want to build equivalents to these spaces, these reproducing kernel Hilbert spaces in the quantum setting. Now, the idea is that you have a exponential in terms of the Q setting. This exponential is always giving you a reproducing kernel in terms of z and omega bar, only that the factorial is now replaced by the Q factorial. Another problem is that this kind of a Q exponential is not defined in the whole of the complex plane, but on a disk with radius 1 over 1 minus Q. That means that you have this Q factorial. You can see the NQ as simply, well, is seen here, 1 plus Q plus etc. Q power n minus 1. And you multiply the 1 by the n2, n3, nq, and get the Q factorial. Now, the interesting is, I have here to say that when k is 0, you recover the Hardy space. with the standard exponential, the reproducing kernel, giving this Q exponential give you the standard reproducing kernel. When Q goes to 1, then this disk becomes larger and larger and becomes the whole complex plane, and you recover the classic Fock space with the classic reproducing kernel. Now, to build a perfect, well, to make a concrete change, you need to introduce the correspondent of the backward shift operator, the Q backward shift operator. And this backward shift operator, instead of comparing F with F evaluated at 0, it compares with F evaluated at QZ, where Q can variate between 0 and 1. Actually, when Q goes to 1, then you recover the multiplicative, the derivative, so you get here again, then this is going to reproduce, it's a scale of backward shift operators which range from the classic backward shift to the derivative in the Fock space. So the Q Fock space H to K becomes the unique operator described in terms of the dual of this Q back shift operator being the multiplicative operator. Also, it satisfies the Q commutator relation, and here you have to be careful because this Q commutator relation has to be understood in the sense that these work on different planes. This relates with quantum mechanics plane or the Manning plane. And for that, I could recommend the classic book of Manning, Non-Commutative Geometry and Quantum Groups, which describe that this relation between the Q back shift operator and multiplicative defines exactly the way how they commute in the quantum setting. So we are going to pass to the structural identities, and I have to accelerate a little bit. These structural identities are based on describing this evaluation of the function under QZ by a gamma Q of F. Then powers of the backward shift, the Q backward shift, can be described as the product from 1 to n, 1 minus qk of this operator divided by 1 minus q power n on powers of the classic backward shift. Now, this now generates a nice idea that you can see what happened to the powers of multiplicative times this Q backward shift operator, these powers, in terms of some equivalent to Q Stirling numbers, multiplicative power k, R power k. So, when you do this, actually this scheme is very easy to follow because it can be generate any kind of decomposition of this form has a very neat solution as was already described by S. Milne in 1978. What you do is simply you have your Q commutator relation that describes the BA in terms of 1 plus Q AB. And now you play the game of interchanging these elements between themselves. And this tells you that this previous sequence of numbers can now be described in an easy way by SQ of 1, 1 being 1. The NN is described in terms of the previous one times Q power n minus 1. And the intermediate ones are given by the Q, the KQ, this summation, times the element, and Q power K minus 1 times SQN minus 1, Q minus 1. Now, this is going to give a very nice table. I have an example for the first elements. The first one is 1, the second is 1Q, the third 1Q cube, but the intermediate element, the S32, is now this nice polynomial of second degree. And the same thing for the degree fourth, you have 1Q6, and now polynomial of degree 3 and degree 5 for the intermediate one. Now, one thing I have to focus here is that these are not the classic Q-Stirling numbers, that these are obtained by the expansion of these powers. So although they do have an interpretation similar of the Q-Stirling numbers, they are not the classic Q-Stirling numbers of first and second case, except if Q is equal to 1. So let me now advance for the reproducing kernels. And the reproducing kernels are going to be described in terms of this Q exponential that I write here. This Q factorial can be described in terms of this Q Pochamer symbol. You can find this in the CAC book that describe these products in terms of a certain element A that you have here and powers of Q, and you make now the product from J, finite product of J, 0 to n minus 1. Now, the 0Q works a little bit like the traditional numbers. 1, the QK is simply summing these powers, and the QK factorial is multiplying these elements as indicated. Now, the Fock space H2K is now going to be the reproducing kernel Hilbert space of functions which are power functions which are analytic in this disk, with the reproducing kernel giving by this exponential evaluated at Z omega bar. Now, the consequences, as I said, you have that Q0 leads to the classic Hardy space, Q tends to 1 leads to the classic Fock, so this gives a kind of scales between the Hardy space and the Fock space. And they can, like the classic Hardy and Fock, these Fock Q-Fock spaces can be characterized in terms of a weighted small L2 space, in terms of this imposing that the square of the small L2 norm in the weighted space is going to be this power series, and that power series has to converge. So to make the connection between the small L2 space and the, let's call it, continuous norm in the L2 space, we have to look into the K-Jackson integral. But the K-Jackson integral has one slight problem. This is not really an integral, is in fact, although it is denoted by the symbol of integration, is in fact a series, and that means that you have to be extremely careful when you make a change of variable here. Nevertheless, we can define for a bounded function in 0 to -1 plus 1 over 1 minus q, we can define the q integral transform simply as the integral in the sense of the q Jackson of 0 to 1 minus q of t z minus 1 f of qt dqt. So this works a kind of Melling transform, but you have to have in mind that this integral is in fact a series of f evaluated at these points with this factor here. So, nevertheless, it acts as the Melling transform in the sense that these coefficients that you have in the small L2, in the weight of the small L2, are now going to interfere in the moment problem because they are calculated as this q integral transform of the inverse of the q exponential function evaluated at n plus 1. And this is actually what happens in the classic Fock space, where the coefficients, the n factorial, is obtained as the Melling transform of the exponential function evaluated at one point, at the point n plus 1. Only that in here you have to be careful. This is a q integral, so in fact it is a series. So let me advance. You can characterize this metric by the measure d nu q in terms of this q-Pochhammer symbol qq and this summation series. But now you have here the classic normalized Lebesgue measure in a circle of radius rq, and the rq is again given in terms of disks of radius q. So you can see this measure acting on unit circles bigger and bigger and bigger. So the space, the q-Fox space, corresponds to space of all analytic functions in this disk, satisfying that the square of the two metric. Now the metric in terms of this metric linked to a mixture of the q Jackson integral and this integral on the unit disks, that metric now links with the weighted L2 metric that you have in the small L2, exactly as you would have in the classic Fock space. So that's why we end up calling Fock space 2Q. But still, if you have something that is kind of a Melling transform, you are interested in convolution type properties. And it's possible to build a convolution between these two, but there is one slight problem. The convolution of the composition is the product of the Mellings of these q transforms, but you have an additional factor, 1 over u 1 minus q power z minus 1, and you don't get rid of that factor. Now, the composition is simply described in terms of the classic convolution between discrete functions, summation from 1 to m, f1 evaluated at q plus 1, 1 minus q, q, m plus 1 minus q. So let's pass to let's pass to some more interesting results. The multiplicative operator is now a bounded operator on the Fock space with a certain norm, which means that this can be seen as a contraction operator. And you can get eigenfunctions for the Q backward shift operator in terms of functions which you get up to a constant, this infinite product in terms of lambda. So this allows you to describe the multipliers for the reproducing kernel Hilbert space. And furthermore, this Hilbert space is the set of all analytic functions in the neighborhood of origin determined by this factor Q, and such that the multiplicative operator is the adjoint of the Q back shift operator. Again, and after a while I will stop writing up to a multiplicative factor, because this multiplicative factor you cannot avoid. It's unique up to multiplicative factors. Now, you also need to, since you have already the multiplicative operator being a contraction, this describes that this Fock space is the branch Rovaniak space. So this is simply spaces, Hilbert spaces, which have a contraction inside that. And these spaces are used in model theory nowadays for operators acting on Hilbert spaces. Also, the classic backward shift operator is bounded in this Q-Fock space. Its adjoint is the multiplicative operator for the R star Q, not for the R0. And it holds, if you pick the monomials that describe the the basis for the L2 in terms of monomials, then the dual of R0 applied to that is AQ minus 1 divided by the Q of K plus 1. That means that the integration, the Q integration, which is a series, is exactly the dual of this operator. That's exactly what is written in this lemma below. So now I pass for results of describing in the Fock space. In the classic Fock space, you have the identity that the adjoint of the derivative is the multiplicative operator, while for the Hardy, you have to combine the derivative with multiplication, derivative, multiplication. Now, similar is going to happen for the Q-Fock space, where the adjoint is simply the multiplicative operator. Well, first, the adjoint of the backward shift, you apply the derivative, and then you apply the multiplicative operator. When you try the adjoint of MZ, then you have simply the multiplicative operator after you apply the back shift, and you have to apply now the Q back shift operator in order to have the adjoint of the multiplicative in the Fock space. Now, these identities are going to characterize the Fock space as before, and that allow us to put the reproducing kernels, this is now a new class of space. You have this, and now you are looking at a variation on the Fock space of the Q-Fock space in terms of tweaking a little bit the coefficient on the reproducing kernel. So instead of having simply dividing by the nq factorial, I divide by nq factorial power square. Again, you're going to have linkage between this reproducing kernel and the weighted small L2 space in terms of coefficients. And when you make the Q, the factor Qk coincides with 1k, the classic Fock space, while 2k can be seen as reproducing kernels for the F2k and this new variation of the reproducing kernel Hilbert space. Now, the interesting part here is that both kernels are positive defined, so the difference is also positive. So no, but the difference is also positive. So this class of space is contractively included in H2K. So you can now define an application which picks the H2K into the Hardy space, into these reproducing kernels with this reproducing kernel, which picks the powers going to be Zn divided by nq factorial. When you do this, then you have an isometry between the Hardy space and these reproducing kernels, and this also allows to make a similarity between the classic identity that you have, that is operator TQ, kinds of commute with the Q backward shift in the sense that it's this operator T applied to the original backward shift operator. Now, this tells you that this map is an isometry between the Hardy space and this space reproducing kernel space FQ, 2Q. Now, it holds that the dual of the backward shift applied to the powers satisfy this integration operator, as you not integration operator, sorry, it's not the integration operator since you have here n, not n plus 1, but it allows to describe also a nice identity, that the identity minus the dual of the Q backward shift times the backward shift is now described as, in the classic way, C star C, where this is the evaluation operator of the function at the origin. Now, this identity characterizes the Fock space, this F2Q, and also indicates that are the 1, 2, 3, the adjoint of the backward shift is an isometry on this space, and is in isometry given exactly by the integration operator. So this now is going to make a kind of introduction to the interesting part, to the final part of my talk, which means you are going to rewrite now this identity in terms of products of matrices. And you can do that So you write the identity 2 by 2 matrices minus RQC and the adjoint of this vector. This makes a positive form, and you can find a Hilbert space and operators B and D such that you describe this identity in terms of BD adjoint of this vector. Now, this operator matrix is coasymmetric, and you have a kind of contraction inside of your space. This is a nice realization, and this nice realization with this SQ, you can now describe the classic part of the Schur analysis, which 1, 2, 3 describe the identity minus SQ star combined on 1 minus Z omega bar. It describes in terms of this product times the adjoint, which is better described here. And this is a nice way of realize that SQ is analytic and contractive in the open disk. So it's a Schur function. Actually, if you look at this, it's kind of similar of when you have a Mobius transformation in the complex plane and you analyze the dy over dz, dw over dz. That's more or less the constant that you have on the matrix on Mobius transformations. So in some sense, this Schur is kind of a Mobius transformation between spaces of operators. It's not correct, but it's a nice way to see it. So now I'm going to pass to the matrix-valued rational Q functions. And the idea is to find realizations for matrix-valued functions that can be expressed in a similar way. How was it? In a similar way as this operator here. So you have a realization for a matrix-valued function if there is A, B, C, D complex matrix which satisfy this. Now, this has application in interpolation problems, but use basically finite matrix theory and finite dimensional space. It has applications in control theory, matrix-valued symbols for Wiener-Hopf operators and Schur multipliers. And you can see it as transfer functions of, well, I have here a nice copy-paste from the internet, a nice symbol of a transfer function for control theory. So you have an input, you have an output, and you have a transfer function that gives you the output in terms of the input. So the problems where they have applications are simple interpolation problems, finding rational functions with prescribed zeros and poles. You have non-homogeneous interpolation problems, find rational functions with specific values at points, and, well, quite a zoo of problems in this case, but I'm having 15 minutes, so I better accelerate a little bit. The idea, if you want to use it in control theory, two concepts are essential. First is the concept that a pair of matrices is called observable if the intersection of the kernels of C powers of the matrix A reduces to the zero. And the second concept is the controllability, which says that a pair AB is controllable if the disjoint intersection, the disjoint union, sorry, of the range of powers ALB is the whole space Cn. Now, with this definition, then you have a matrix realization in terms of this set DAB, where D is again the evaluation of the matrix function at the zero. And the important part is that if the pair CA is observable and AB, so CA is observable, AB is controllable, the triple is called a minimal, and this tells you minimal realizations are unique up to a similarity matrix. So work a kind of equivalent classes, but you can obtain the results rather nice. So another lemma that we need is that a matrix valued function is rational if it can be written in terms of C, identity minus CA, inverse of this, times P. So you can describe this in terms of powers of CA, and you get the need for the controllability and observability of your system. So you pick f of z to z of r to write it in this way. Pick z0 gives the evaluation at the origin to be 0, and now you divide both members to z and you obtain this description of your matrix. Now, applications. One is exactly the polynomial characterization of these matrix valued polynomials, as long as you can describe it in terms of a scalar polynomial which is non-zero at the origin. Another comes at the realization that you can use it for control theory, making controllable and observable and controllable matrices. And another is on Hankel operators of Hankel operators, which you know it's operators where the diagonals in, well, these non-diagonals are fixed. So F0, F1, F2, F3, and this operator can be described very easily. You can obtain these coefficients in terms of the realizations of these matrices. Now, these Hankel operators appear in the study of PMO spaces and are a kind of how to approximate operators by finite polynomial description. And that is exactly what happened. These coefficients arise as elements on the Taylor series, where the coefficients are simply CAKB. For these matrices, CAB, actually, I always find strange as in control theory, they write CAB instead of ABC, but that's traditional in control theory, so I'm not touching that. So they appear as coefficients of these powers on this realization of the matrix of the realization, and allows you also to characterize in terms of the backward shift, simply that the linear spans of this is simply a finite dimensional space. Actually, this is also the basis for later building a kind of Jordan chains, but maybe I pass the recall on the Q calculus because it's main plane, commutator relations, different settings. So you have the Q-Fock space H to Q in terms of this reproducing kernel built with the exponential. You have the linkage between the classic Hardy space and the Q-Fock space. And, well, one recommendation, if you are interested in this field for sampling on the Q-linear grids, is the work of Daniel Abreu of 2006. So, you have the Q backward shift. You know that the backward shift for the Fock is the derivative. The backward shift classically is this quotient. And now you want to see what happened for a finite matrix with radius 1 over 1 minus q, such that this series is this product. If you have this, then the series is described in terms of this infinite product, where this is elements, and you see that this infinite product is quite similar to the infinite product in scalar part. Well, this is a matricial infinite product, while this is a scalar infinite product, but they have rather similar properties. So, you now are going to build, you are going to build now the set of any dimensional subspace of matrix Cn valued functions, analytic at origin, and let f of z be the matrix valued C small n big N, such that the columns are bases for this space. Then this set is RQ invariant if and only if there exists a matrix which depends on the Q and has dimension n by n, such that you can write Fz as the product, infinite product of elements similar to what you have here, but now with the evaluation, the matrix evaluation at the origin of the function f. Now, if you now define the Q observability operator, which is simply applying this to a certain vector x, then this space is RQ invariant if and only if it is the range of a Q observability operator. Now, this has a nice idea to build, first, to construct operators such that this Fock space is a reproducing kernel of analytic with the dual implies the dual of the multiplicative being the Q backward shift implies that this M space is invariant for the multiplicative if and only if the orthogonal of the space is invariant for the RQ, for the backward shift. There exists an operator such that Q backward can be seen as commuting, F commuting with A, F of Z A, and F of Z is the evaluation times the infinite product, And conversely, these satisfy the commutation between this observability operator acting on the left, the Q backward shift is the same of having this operating acting on A. Now replacing A with RQ and C with the evaluation at 0, then we can consider, well, one bracket too much, this nice operator for control theory. The last nice part is that this valuate analytic at the origin is called RQ cyclic if the linear span of the columns of these functions is finite dimension. And this means that this function analytic at the origin is RQ cyclic if and only if it can be written in this form for a certain triple of matrices. And now you can play again the game of observable and controllable. Now, I think I'm okay. Q. This is going to pass this one. I have the Borel transform and I have the Borel transform. You can write a Q Borel transform in terms of the powers zk averaged by the Q factorial and now the coefficients fk. But you have to be careful because this is different of the isometric Q Borel transform because that one has a square root of this Q factorial. Now, properties, I think I'm going to pass. Maybe not because I want to describe here the analytic function. The Q Borel transform is an analytic function in the disk averaged by this. And the Q backward shift applies to F simply as the traditional backward shift applied to Borel of Fk. So F is a k-rational matrix if you have Borel Fk is a classic rational function. So this now allows you to obtain span of these elements, RQ, or powers of the Q backward shift applied to T, and you can write the block-Hankel matrices in terms of T0 on 0 times Q factorial and 0 Q factorial and so on. So you get a Hankel block describing this element with finite rank. Now, let me part characterization. No, better go for the Jordan chains. Now, the idea is to get now the equivalent of Jordan or of generalized eigenvectors simply by picking the realization of your function and see if you can write in terms of n eigenvectors, and such that the invariant finite dimensional space is simply this Q matrix applied to a vector C. Now, under this, we are going to assume that CA is observable, and you say that you have a Jordan chain if and only if this AQ is a Jordan cell. That means that you have eigen vector for this element. And I think I'm about to finish. I have here an example where A is a very simple matrix, identity plus n, 0, 0, 1, and n squared is 0. Then you have that this inverse is easily described. And when you have the evaluation at the origin being this, then you have your base described in this nice way. So the first base 1, 0 is given in these terms. The base for 0, 1 is given on these elements coming out of the product. So I think I'm finishing. And now just references. First, the original paper of Jackson in 1910. There was a nice monography that nowadays everybody uses from CAC of 2001, but you have to be careful because this Q calculus was quite a hot topic in the 70s and the 80s. Milne is quite one nice paper where he described how you generate this sequence of Stirling numbers or type of Stirling numbers. These first results come from this paper with Daniel Alpay, Uwe Kehler, and Baruch Schneider in 2024. The part of control theory, there is this nice book of Paul Goldberg and Rodman of 1919. It's a very good book for somebody wanting to learn on control theory in terms of matrix valued functions. And finally, this last part comes from this nice article in Integral Equation and Operator Theory. So thank you very much. And let me stop the sharing.
Thank you very much for your nice talk. For questions, please raise your hand, virtual hand, and the technical support will activate your microphone. For question or commentaries, anyone? Okay, I have a question, but it's let me on the chat. Okay, Tobias Castro. Is there any relationship between this Q function and the KP hierarchy?
I have no idea because KP hierarchy, well, I didn't heard about it. I'm starting on control theory and I have no idea if it has. Can you elaborate a little bit more on QP hierarchy?
Tobias Castro, please. Okay.
These Q functions are related to the quantum system and that I know they have relations with the Manning plane. They have relations in, actually it's one particular case of fractional derivatives, very particular, but yeah.
Okay, thank you. Okay, let me ask you something quickly. Just like a curiosity, in this analysis you have shown to us about reproducing kernels. Can be it extend to several complex variables or not?
They are complex variables. Wait.
Okay.
Depends. The first part was on complex variables, but the second was on matrices, on functions, matrix values, but the values were taken on Cn So complex,
Mm,
several complex variables.
okay. Okay, thank you. Okay, thank you so much.
Thank you
Dear
very
colleagues, thank you so much. Dear
So
colleagues,
thank you too.
okay.
And let me,
Now I pass the sharing duties to the Dr. Yuriko Pitones from Mexico, who is board member of ICMAM Latin America, and this year was in charge of the program of Women in Mathematics of ICMAM, supported by International Mathematical Union. So please, Yuriko. You are muted, Yuriko. Dua.
Yes, now Yuriko has permissions, yes.
Okay, thank you. Good morning, afternoon, or evening for everyone. It's a pleasure for me welcome you to the second talk to this event. We are honored to have Professor Carmen Judith Vanegas with us today. Hello, Professor. Thank you for accepting the invitation. Please, maybe you can try to share your screen. The microphone of the Professor Carmen is.
Okay, now I think Professor Luis Vanegas can share.
Yes. Hi. Good morning. First of all, I would like to thank the organizer of this conference for inviting me to give a talk. Thank you. I will start by answering the question about strategies. Here, I think so. What happened?
Is your screen?
Yes.
Okay.
One moment. Here. Yeah. Now, about strategies to make visible the work of female mathematicians in Latin America and the talent of young women. I have three ideas. The first one is the schools or meetings organized by centers, societies, or unions of mathematicians invite and provide financial support to female mathematicians who live and work in Latin America to give courses and conferences about their mathematical work. My second idea is free costs for publications in open access scientific journal for women who live and work in Latin America. And the third idea is to provide scholarships to mathematical centers, societies, or organizations to young women living in Latin America to study doctoral programs in mathematics or becomes involved in postdoctoral programs in mathematics. Okay, it is all. Now about my talk.
Okay, let me introduce quickly
Yes.
your
Okay.
person and your talk. So Professor Vanegas is a tenured professor at Universidad Yachay Tech in Ecuador. She obtained her bachelor's degree in mathematics from the University of Zulia in Venezuela and a PhD in natural science with a focus on mathematics from the University of Halle-Wittenberg in Germany. Over her career, Professor Vanegas has held important administrative and academic positions, such as Vice Dean of Research, Postgraduate Studies, and of Research at the Technical University of Manabí in Ecuador. She has also served as a coordinator of the master's program in mathematical research at the postgraduate institute of the same university. Her research covers fundamental areas, has complex analysis, partial differential equation, harmonic analysis, and Fourier analysis. Today, she will speak to us about weighted direct operators. And Professor Venegas, we are excited to hear what you share with us.
Okay,
Please.
thank you. Thank you, Yuriko. Thank you. Well, I'm going to talk about weighted direct operators. And one motivation to study this operator is the problem of heat conduction in anisotropy media, and it is the thermal conductivity of the materials depend on the direction of the heat flow. While the problem of non-stationary heat conduction in isotropy media has been investigated widely in mathematics and physics by studying this associated differential operator, the problem of heat conduction in anisotropy media is a more general and is of the interest in physics and engineering. Materials with this anisotropy nature and problems of heat conduction in this media, you can see always, or you can always consult this reference of Han and Osisic from 2012. When the thermal conductivity is constant, the associated anisotropy heat operator is in this form, derivative of T minus the divergence of B times the operator nabla, where B is a symmetric and positive definite matrix, and the interest represent the thermal conductivity coefficient of the media. In Clifford analysis, the study of the solution of boundary value problem for some type of second-order differential equation, those usually in mathematics and physics, is done by means of a factorization by a differential operator of first order and with help from Clifford algebras. These first-order operators are of the generalized Cauchy-Riemann or Dirac type and their variants. In this reference of Bernstein from 2006, factorization of the nonlinear Schrödinger equation and applications, and references therein are shown different type of second-order operators, factors by operator of the Dirac type. If we have a fundamental solution of these first-order operators, the solutions of the boundary value problems are obtained by means of the integral representations given by integral operator Teodorescu or Cauchy-Bizassi type or certain projection operators. My talk will be divided into following points. First, once preliminaries, 2 weighted Dirac operators, 3 fundamental solutions, 4 Cauchy-Pompeo integral formula, and 5 concluding remarks. What about Clifford algebras? We consider an orthonormal basis of R to n, and we denote A sub n the 2 to n dimensional Clifford algebra with basis given by beta. And here the subindex n is equal n1 times nr, satisfying this relation, this ordering relation. E0 is the identity element, and this equality is satisfied. We know that in this algebra, the multiplication is given by this rule, where this is the famous Kronecker symbol. The involution that we use is the Clifford conjugation defined in this form, where this is the cardinality of n. And this involution satisfies these two equalities. If we have a domain in Rn and we denote this domain by omega, functions with values in this algebra a sub n and defined in omega can be written in this form, and these are real value functions. And we say that this function U have property of continuity or differentiability if its component have these properties. More about Clifford algebra or some results from Clifford analysis, you can consult in this famous book from Prax, Delange, and Somen, Clifford analysis, and also in Spanish from this book from 2008. What about the operator delta tilde? We define this operator delta tilde as the divergences of B times the operator nav. And these B sub ij are the entries of a symmetric and positive definite matrix B, and this matrix is n by n. Since B is a SPD matrix, then there exists its inverse matrix and its square root are, and they are also SPD matrices. And besides the square root of A is a square, this is a B up minus up 1/2. And if B is the decomposition into singular values, then the square root of B is given by this other decomposition. Now we consider a Dirac type operators with weights, where the weights gamma sub I are appropriate constants in A sub n, such that this operator factorizes the second order elliptic differential operator delta tilde n. To simplify the calculation, we will write this weighted Dirac operator and the conjugation of this weighted Dirac operator in this form, where psi sub I is equal to gamma sub I multiplied E sub I. Calculating directly these two products, we obtain these two equalities and equalize this expression to this operator delta tilde. It followed that this operator, weighted Dirac operator, factors to this operator if the weights psi sub I fulfill this relation. We call this relation 1 and 2. Note that if the weight psi sub I is equal to E sub I, then the structure relations above are reduced to this, which implies that the classic Dirac operator in the algebra A sub n factorizes the operator delta tilde only in the case where B is the identity matrix. The question now is how to build the weights. The construction of the weight is based on that it is possible to make a decomposition of the coefficient matrix B in the form B equal L transpose, where L is a matrix n by n. For example, the non-Koleski decomposition, where L is a lower triangular matrix, or L is the square root of B, and so on. Given any of this factorization of B, if we define the weights psi sub I as the ETH row embedded in the standard basis of Rn, then these weights meet the structure relations 1 and 2. Yeah. The basis we take to construct the weights tree, I mean these weights, is composed of vectors in An. and therefore the weights are vectors. Operators of dirac with weights in the quaternions and factoring the Laplacian were introduced by Shapiro and Vasilevsky in this paper from 1995 and in the so-called psi-hyperlomorphic function theory. This theory was the key to the construction of a generalization of the P operator in the quaternions. See also this reference from Gurleve, Keller, and Shapiro from 1999. We can also construct ways in this algebra that do not necessarily have to be vectors. We will illustrate this point with a construction of a non-trivial example of a weighted Dirac operator with a weight tipswise satisfying this relation 1 and 2. To do that, we need some definitions. We start with a definition of this set gamma sub n up to 0 equal to the sets from sub-indices belong to the gamma sub n such that the cardinality of n is congruent to 1 module 4 or is congruent to 2 module 4. And take a known subset of this, and we denote this gamma sub star minus, such that for all elements in this set, the symmetrical difference belongs to this set gamma sub n up to 0. Now we consider a subspace from this algebra defined as degenerate by the set E sub n such that n belongs to the set gamma sub n minus and gamma sub n minus E0 union gamma sub star minus. Well, and we consider these notations. If the Clifford conjugation is restricted to this subspace, to this, it has the following properties whose proofs are obtained from a Dirac calculation. Okay, here this bracket means the scalar part of the element, and here this bracket means the vector part of this element. Now we define the weight Psy as the ETH rho of L embedded in the basis of this subspace. Its mean Psy is defined by this expression given by 4. Then, applying the above properties given by the lemma to the left side of 1, we obtain this equality. Now we will show an explicit example in the case n equal 3. We consider, for example, this operator delta tilde in R3. We take the coefficient matrix, and it is given by this symmetric matrix, and we apply the Cholesky decomposition to this matrix in the form L times L transpose, where L, after some calculation, is this matrix. Now, if we take as basis for this space E0, E1, E2, and E3, and we apply this, we obtain the weighted Dirac operator in this form. Okay? In view of the lemma, other bases that can be considered for this space. For example, the basis E0, E1, E12, E13, or E0, E3, E13, E23, and for all these bases, we obtain the operator that also factors the operator delta tilde in R3, and they are these operators. Now we define for 2 points C and X of Rn and no Euclidean distance rows by this definition given by phi, where A sub ij are the coefficients of the inverse matrix of the coefficient matrix. We can prove that a fundamental solution for this operator delta tilde n is given by the parametric Newton kernel defined in this form. Here, omega sub n is the area of the surface of the n-dimensional unit ball, and this is the determinant of B. The proof of this, that it's a kernel or the fundamental solution for this operator, you can see in these two papers from 2015 and 2022. Applying the conjugation operator, D bar, or the conjugation operator of the weighted Dirac operator to the kernel, to the parametric Newton kernel, we obtain this function E sub W defined in this form. And because this operator factors the operator delta tilde, then this 6 is a weighted monogenic function for each x different of C for the operator, for the weighted Dirac operator. And we can prove also this estimation, and this estimation shows us that the function E sub W is weakly singular. Now we have the green integral formula for the weighted Dirac operator D sub W. As usual, V and U are functions defined in a bounded domain in Rn with values in the algebra A sub n, and they are continuous differentiable functions. And here, D sigma is the surface element in the coordinate system psi sub 1, psi sub n. If we take V as the function E sub W, I mean this function, and if we take the domain omega sub epsilon, which is the domain omega minus this neighborhood of C, then the green integral formula becomes in this other formula given by Knight. And if we take this term and we take the limit as epsilon tends to 0, we can prove that it is equal minus U of C. And you can see this proof in this article from 2018. Now, if we take for all this equality limit as epsilon tends to 0, we obtain the Cauchy integral formula, Cauchy-Pompeo integral formula, which is this. Here we use this result, and we use also the E sub W is a singular, is a weakly singular function. And here, if we suppose that U is a weighted monogenic function, it is 0, and so its integral is 0. And we obtain the Cauchy integral formula for a weighted monogenic function, and it is this. Okay? Wow. I am weakly, excuse me. So, concluding remarks. Well, in this chapter, the author introduced in 2008 the Clifford algebra depending on parameters. In this algebra, they worked with a non-Euclidean metric depending on the parameters, and therefore this algebra represents the most mature underlying algebra to be used in the decomposition of this operator. Even more, to factor this operator considering Dirac operator with weights, the necessary underlying algebra to achieve it remains the parameter depend one. Because, why? Because the weight must satisfy this structure relation. That is the reason. In this other article from 2020, a theory of integral operator for the Clifford type associated algebra depending on parameter was presented as a generalization of the theory of integral operator for the classic algebras, classic Clifford algebras. Fundamental for the development of initial volume problems involving the generalized Cauchy-Riemann operator with real constant weights and for functions with values in a parameter-dependent Clifford algebra can be seen in this paper from 2013. In the same context, a Dirichlet problem has been studied for the case n equal 2 in this paper from 2015. In the work from 2022, the authors have studied the anisotropy Helmholtz operator, and from this operator, they showed a fundamental solution under the framework of the complex quaternions algebra. Recently, in this work from 2023, the author have factored the non-stationary diffusion operator for anisotropy media, and to do that, they use parabolic Dirac operator defined on parametric Clifford algebras. And that's it. Thank you. Gracias, Yupachani. I think
Thank you so much
I
for
will
your
hand.
wonderful talk.
Okay.
And
If you have any
now,
question or commentaries, okay.
yeah, we have time
I-
for question or comment. And if the audience has any question, please raise your hands. Professor.
I have a
Yes.
question. It's thank you for your interesting talk. Have you considered treatment by semigroup properties? Since you
Riemann.
are working using as a base a modified heat equation, you can use perhaps you can use semigroup properties to describe your solution.
Yeah.
But
Yeah.
of course, you will need to have kind of circular domains. You will have to be careful on that, but should be able.
Yes. Okay. No, I don't. We do not consider this, but okay. I thank you. I will think about that, Paula. And great to see you.
Duban, do you have a question?
Yes, I have a question. Okay, maybe I will move to Spanish. Profesora Carmen Judith, muchísimas gracias por participar, por aceptar la invitación de las organizadoras del evento de ICMAM. Bueno, también me da mucha alegría verla después de el evento de Brasil. No, quería solo agradecerle por la charla tan inspiradora también y de pronto preguntarle si puede comentarnos sobre algunos problemas abiertos.
Yes.
Types of
Okay.
open problems.
Yes. Okay. Thank you, Duban. Well, now we work in two problems. No? I'm working from this weighted Dirac operator applying to the Rarita-Schwinger operator or Rarita-Schwinger equation. We have some results about that. We could obtain a kernel from this Rarita-Schwinger operator using, or Rarita-Schwinger equation using this weighted direct operator, but we have not published now still. And well, this is now. This is I am working in this problem. Okay, if some have some interest, I can send papers, or we can contact me by email and we can work. This is it's no problem for me.
Oh, thank you very much.
So another problem that I'm working is hyperbolic numbers. We can try to fix initial volume problem in the context from the hyperbolic numbers. And I know that hyperbolic numbers has been also studied widely, but it does depend on the metric that we use, and then that I'm concentrating this with one of my students.
Wonderful. Thank you very much.
Yeah, thank you.
At the chat, we have a question for Blanca Radillo, and she asked, how far can you extend this when you consider a more general second order elliptic equation?
Well,
What I mean, non-symmetrical.
Yes, I'm not considered from high order elliptic equation, elliptic operator. No, I was working only in the second order operators. Okay.
Okay. Another question or comment? I have a question in this chat. In these Cauchy formulas that you have considered, the boundary is smooth enough. Have you considered the case of less regular boundaries, like Lipschitz ones, for instance?
Well, I think, I don't remember exactly, but I think we consider this in this paper in this paper. I think I consider this in this. But in this paper, we also prove a Cauchy integral formula. Okay, you can read this in this paper.
Okay, thank you.
Welcome.
More questions or comments for the audience? No?
Well,
No, thank you very much.
May I let up to come to, well, I can so.
Okay. Thank you, Professor Vanegas, for accepting this invitation. It was a pleasure for us.
Also for me. Thank you. Bye.
Thank you so much. The next talk will be start at 4 p.m. in CET time. And now we have a video or something. Karina, you have. Oh,
Yes.
Thank you.
Yeah, exactly. Thank you.
En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso. En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua, y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso. En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza.
El proyecto Visibility of Latin American Women Mathematicians, aprobado en febrero de 2024 por el Committee for Women Mathematics of the International Mathematical Union, busca visibilizar a mujeres matemáticas de Latinoamérica entre grupos de niñas y jóvenes de escuelas rurales, con el fin de concientizar que, sin importar fronteras, las mujeres matemáticas realizan grandes contribuciones en la ciencia y la industria. El objetivo es impulsar modelos femeninos a seguir en las carreras STEM y principalmente en matemáticas, para que las niñas de hoy y las mujeres del mañana tengan mayores posibilidades de alcanzar sus metas y aspiraciones, considerando como una posibilidad ser científicas.
Me acuerdo que en mi salón de clases de la primaria, al menos la mitad de los estudiantes éramos niñas. Luego en la secundaria, preparatoria y en la universidad, la proporción aumentó. De hecho, en mi generación de licenciadas en matemáticas, nos graduamos solo mujeres. Pero cuando pienso en el terreno de las ciencias y las matemáticas, me pregunto, ¿cuántas mujeres se desempeñan profesionalmente? Las cuentas no me cuadran. No recuerdo que en mi niñez me hayan acercado especialmente a las matemáticas. El entorno escolar no me preparó para indagar en el terreno académico y matemático. Si pienso seriamente, No encuentro los caminos ni las vías que me han traído hasta aquí. Tal vez me convertí en matemática por casualidad. Lo cierto es que fue y es una fortuna, porque si me transportara al contexto escolar en el que crecí, debería estar haciendo algo distinto. Lo que he dicho hasta ahora no es una queja ni un reclamo, sino una reflexión sobre lo que acontece en la escuela. El sesgo no solo ocurre en la formación académica, también en el entorno familiar y social. ¿Por qué pasa esto? Quizá porque se piensa que las matemáticas y las ciencias solo pueden ser practicadas por hombres, como los deportes, y entonces, por omisión, somos descartadas como futuras matemáticas y científicas. Nadie nos impulsa ni se ocupa de revelarnos que podríamos dedicarnos a las matemáticas, astronomía, física, química, medicina. Según un estudio de la Organización de las Naciones Unidas, en 14 países, la probabilidad de que las mujeres obtengan un grado de licenciatura es del 18%, 8% para un grado de maestría, y solo el 2% logra un título de doctora en alguna materia relacionada con la ciencia. La representación de mujeres en las carreras científicas es del 28%, frente al 72% de los hombres. ¿Qué tenemos que hacer para que estos números y nuestras realidades cambien? No tengo la respuesta, pero estoy segura de que la sociedad en todos sus niveles debe motivar el desarrollo científico en las niñas. Debemos hacerlo para no seguir desperdiciando el talento y las ganas de niñas y jóvenes. Así, en el futuro, podremos tener una ciencia vasta, gigante y más justa. Desde donde estamos, un grupo de mujeres matemáticas latinoamericanas buscamos impulsar y motivar a las niñas a ser científicas. El mensaje es claro y sencillo. Es importante conocer y reconocer a las mujeres matemáticas que se desempeñan profesionalmente hoy en día, que sean mentoras y modelos a seguir. Pero es más importante que nuestro mensaje llegue a todos los rincones de nuestro país. Cuando les preguntamos a las niñas ¿a cuántas mujeres científicas conocen? Algunas responden Marie Curie, y es que Marie Curie es nuestra heroína. Pero cuando les preguntamos ¿a cuántas mujeres matemáticas conocen? Hay un silencio prolongado y miradas buscando respuesta unas con las otras. Si hoy volvemos a hacer esta pregunta, las niñas con certeza responderán.
Hola, soy Yadira Valdivieso, soy matemática mexicana y hago teoría de representaciones.
Hola, ¿qué tal? Soy Verónica Redondo y actualmente trabajo también para el Senado de la República en la Secretaría Técnica de la Tesorería.
Hola, soy Ruda Alejandra Torres, matemática colombiana. Actualmente soy directora del programa Matemáticas de la Conrad Lorenz en Bogotá, Colombia.
Soy Rosibel Pacheco, matemática hondureña, presidenta de la Asociación Matemática de Honduras.
Soy Rita Jiménez Royand, matemática mexicana y soy investigadora en el área de topología algebraica.
Hola, ¿qué tal? Soy Raquel Perales, soy una matemática mexicana y mis áreas de investigación son la geometría riemanniana y el análisis geométrico.
Hola, soy Pati Jiménez, soy matemática mexicana. Trabajo en la Universidad Autónoma de Zacatecas.
Hola, me llamo Pamela Estefanía Harris. Nací en Guadalajara, Jalisco, México y he vivido en Estados Unidos desde los 12 años. Soy matemática y mi investigación se enfoca en la combinatoria algebraica.
Soy Nancy Gelman, matemática de nacionalidad argentina y trabajo en Uruguay hace muchos años. Me dedico a los sistemas dinámicos y acciones de grupo.
Soy Marta Mendoza, soy una matemática mexicana. Mi área de estudio es la teoría algebraica de números, pero también me interesan la historia y la divulgación de las matemáticas.
Hola, soy Marta Álvarez, soy matemática que trabajo en Guadalajara.
Hola, soy María Isabel Cortés, matemática chilena y trabajo en las áreas de sistemas dinámicos y teoría de grupos.
Hola, soy María Chara, soy docente e investigadora de CONITEC en Argentina, la Universidad Nacional del Litoral, y me dedico a la teoría de código.
Soy Luz María García Ávila, matemática mexicana e investigadora en el área de teoría de conjuntos.
Hola, soy Leticia Brambila Paz, mexicana, trabajo en geometría algebraica, en particular en espacios módulos sobre haces vectoriales.
Soy Leslie Campa Raimundo, matemática mexicana.
Soy investigadora en el área de mecánica celeste, particularmente en configuraciones centrales.
Soy Laura Rocío González Ramírez, matemática mexicana, y soy investigadora en el área de matemáticas aplicadas a biología y medicina.
Hola, ¿qué tal?
Okay. Okay, the Professor Jacqueline is here. Welcome. Okay, we will continue with our program, the first day program. And the next speaker is the Professor Jacqueline Godoy Mesquita. Jacqueline Godoy Mesquita is a distinguished mathematician. Currently, she is professor at the University of Brasilia. She completed her PhD in mathematics in 2012 at the Institute of Mathematical and Computer Science, ICMC, at the University of São Paulo, including a research period at the Academy of Science of the Czech Republic in Prague. The Professor Jacqueline has received numerous accolades, including the International Bernd Auerbach Prize for students from the International Society of Difference Equations in 2012, and the For Women in Science Prize, awarded by L'Oréal UNESCO and the Brazilian Academy of Science in 2019. She was also honored as an Oberwolfach, sorry for my bad pronunciation, Leibniz Fellow in 2018, and selected for the 5th Heidelberg Laureate Forum in 2017. She has been an elected member of the World Academy of Science twice, LACREP, and the Brazilian Academy of Science, and she served as Vice President of the Brazilian Mathematical Society from 2021 to 2023. In 2019, she was a Capes Alexander von Humboldt Fellow at Justus Liebig Universität Gießen in Germany. Today, she will talk about functional differential equations with state-dependent delays, an overview and new trends. And she, as a female mathematician, will share with us how she perceived the challenge faced by women in the community when trying to make their way in the academic field. Please, Professor Jacqueline, you can start.
Thank you very much, Karina, for this nice introduction. I will only share my screen just a second. Oh, sorry. Just a moment. So oh, yeah. I think now you can see, yeah, my screen. So,
yes.
Okay, nice. So first of all, I would like to thank the organizers for this invitation. It's a great pleasure to me to participate on this event. And as was mentioned, I will talk about state-dependent delays. It's a part of my field. So, okay, and this work was supported by Alexander von Humboldt and Capes. And the outline of my talk, I will start with some motivation to investigate this type of equations. Then I will talk more about the neutral type of these equations, neutral functional differential equations with state-dependent delays. Then I will talk about functional differential equations with state-dependent delays, and I will finish with some open problems. So this work will be based in two works that I made, one with my co-author, Professor Bernhard Lani-Weida, from Justus Liebig University in Germany, and the other one from my former PhD student, Henrique dos Reis, and my co-author that unfortunately passed away, Professor Hernan Henriquez from Chile, so in memory, and it will be based in these two works. So I will start with some motivation first about these types of equations. So I will start with some timeline, some history about this field. So first, when we think about, for example, type of population models that usually it's very, many people works on that direction, what we have is the following. So we have that the logistic equations are very famous. You know, like we learned about logistic equation when we start some undergraduate courses. We learn one of the first models about populations, this type of logistic equation. But then Hudson was one of the first to realize that the Hudson equation was nice, but there were some problems because it does not take into account the time between the birth and the enter in the maturation process. And this time needs to be in the equation. So here Hudson changed it a little, the logistic equation, and put here, if you see this tau that appears here. So it seems a very small modification when we have the logistic equation and this Hudson equation, only this tau, but this makes a lot of difference when we see about the dynamics and the behavior of the solution. So here is the behavior of the solution of the logistic equation, and here is the behavior of the solution of Hudson equation. So that small delay that we saw before, it can change a lot the behavior of the solution. So that's why it's really important to bring into account when we have this delay effect in the equation, because the behavior of the solution can completely change when we put this delay. And we have several populations that indeed has this type of behavior, like oscillatory behavior. So, but okay, so here is one motivation for we have the delay in the population models, for example, or in many types of models, we can think that it's really important to consider the delay, not only in population models, but any model that we have some time in between the cause and effect. So, for example, anything that you think almost all the phenomena will have this time in between cause and effect. For example, so if you have taken medicine, so we know that the effect of taking medicine, it's not instantaneously, but it takes time in between to have take the medicine and it starts to do some effect. Also, we can think about epidemiology. For example, the COVID-19, we again know that there is an incubation period for this disease. And this incubation period should be viewed as a delay. So the time in between you take the disease, and there is one time in order to present the first symptoms of the disease. So this incubation period also can be viewed when you put in your equation as a delay. So this is really important, and we have many phenomena in that direction. However, here I would like also to talk not only about this type that we saw here, that's constant delays, but more different types of delays, that's delays, state-dependent delays. So it's a delay that's not constant, but it's a function which depends on the state. So it's really important to take into account. For example, in the population model, we know that considering the population, not all the population will take the same time in between the birth and entering the maturation process, but it will change accordingly with other factors. So again, it's not very good to consider, let's say, constant delays, but state-dependent delays. So here we have that Rodney Driver. He was really interested about some two-body problems, but in electrodynamics. And he realized that when we deal with electrodynamics, we really need to consider the delay in this type of a problem. So when we have the two-body problems in celestial mechanics, that's okay not to consider the delays. However, here, when we are considering the two-body problems in electrodynamics, it's really important to consider the delay. And more than that, the delay here needs to be state-dependent delays, because it depends, of course, of the position of the bodies that you are considering, for example, the planets or anything in that direction. But here, of course, since you are in electrodynamics, we are considering like atoms and something like that. Also, in the population model, as I mentioned before, we had this tau constant. However, after many scientists realized that it was not completely okay to consider only the delay constant, because the time in between birth and entering the maturation process is not constant, but it depends on the state. So here again, these three authors, they realized that looking for some populations, seal populations and whale populations, and they realized that the length of time to maturity is a function of amount of food. So really take into account, it's really important to have state-dependent delays in that sense. So here they brought a much more sophisticated type of model. Here we have this tall that depends on the state. So we have this type here. And here now we have this population model. So they published this in this paper. And here we have much more realistic model, since we are considering not constant delays, but delays depends on the state. And here is very nice to show a little about the behavior of the solution. And considering like the state-dependent delays in this interval here, we again have that it's very oscillatory. And here is for the constant delays. And one can see and think, okay, but it's not so different when you consider like constant delays and when you consider like state-dependent delays, because if you see here, it's almost the same in that case, and it's much more complicated to deal with state-dependent delays instead of constant delays. However, here is a specific case that, okay, it's almost the same, the behavior. However, when you deal with state-dependent delays, you can change completely the behavior of your solution. So recently, I am working in a problem that is exactly that. We are investigating what's happening about the stability. And you can have, for example, in some types of problems that if you have a constant delays, your solution can be stable. But if you have like state-dependent delays or time-dependent delays, you can lose completely the stability. And in the other way around, you can have like an unstable solution for constant delays, and you can have stable solutions for state-dependent delays. So again, it's really important to consider the state-dependent delays in order to have a more realistic effect and dynamics in the behavior of your solution. And here is really important, again, when we consider like a population dynamics, to considering that this delay depends on the state. So here again, we have many authors that realize that when you deal with this type of population models, you really need to consider state-dependent delays instead of constant delays. Okay, so now let's see a little about these types of equations. So we have a lot of motivation, as we can see, to investigate this type of equations. However, it's not so easy to deal with state-dependent delays. So let's see a little how it works in terms of regularity, how to deal with this type of delays. So here is a type that we have differential delay equations with state-dependent delay. So here we have that all depends on this function here, this x of t. And here it's really important to mention that this x sub t is not a partial derivative, but here we consider it as a function that depends on this interval. So it's a function defined here for some theta. So it's a space of functions. So here we have a type of state-dependent delays. And one thing that is really different when you deal with state-dependent delays is that it's very hard to obtain the uniqueness of solution when we have state-dependent delays, especially if we consider the initial data in this space. Also here, it's really important to mention that when you deal with delay equations, our initial condition is a function. So that's why we are taking it in this space. However, if we take our initial data in this space, what's happened is that it's really hard to ensure that the uniqueness of solution in this case, when you're dealing with state-dependent delays. However, when we have like constant delays, it's not the case. It's not so difficult to ensure the uniqueness of solution. So here is an example that we look, and if we see, we really think that it could be very easy to ensure like the uniqueness of solution. However, it's not. So here, we have this equation that's a very simple state-dependent delay equation. So here is the delay that depends on the state, and this is our equation. And if we consider here our initial values in this way, so this function here, we can have two different types of solution here. So both functions are solutions of our problem. So here only to show that's not so easy to have to ensure the uniqueness of solution. So, and why that's happened? So, and here we will see that it will not be easy to transfer all the results that we have for these type of equations to state-dependent delays. And the main thing behind is because to have a disconnection between this equation here and the equation using like state-dependent delays, the things that we need to have this evaluation map. And this evaluation map does not satisfy some irregularity. And the main thing is that our F0 here, when we define it in this way, using the evaluation map, we cannot ensure the smoothness of our F0, and that's why. So here, as we mentioned that in order to get this equation here, we use this evaluation map. And what we have is that it's not, in general, it's not continuously differentiable. And because of that, we cannot translate all the conditions from one side to another with a good regularity. And that's the big point here. So now I will talk about the main problem that we investigated in this case, and I will try to bring some motivation behind that. So we investigated about one model that's for exchange money. So the fluctuation of the market about, we have euro, dollar, and so on. So we know that there are some the market needs a time to react. And when it happens, we know that the euro or the dollar will be like, can be more valorized or not, like, so here, exactly in this case, Brunovsky, Erdely, and Walter, they brought this type of model in order to bring this to reality. And they consider a delay, that's the time in between to the market react, and there have this change about the money fluctuation. So here was the first model that they considering. And here, if you see, we have only a very simple type of delay, like constant delay. Here, the delay is constant equal 1. But even in this very simple case, it was really hard to deal with this type of problem, because it's really hard to deal with delay equations, even in the constant case. And in this paper, because of many difficulties in order to understand the dynamics, the solution, the asymptotic behavior of the solution, they made a lot of conjectures about the asymptotic behavior. Later, we have that Walter proved many properties concerning periodicity and bifurcation for the solution. And then we have that Garab, Kovacs, and Christine, they proved many of the conjectures, what appears here in this paper from Brunovsky, Erdely, and Walter. Then Stampfel was one of the first to realize that in order to bring a more realistic model, you need to consider not only constant delays, but state-dependent delays, because again, it's not constant, the time in between, in order to have this fluctuation. And this time depends on other factors. So he brought this equation here. And then later, we have that Walter realized that more than that, it was needed to have this derivative here in our x. So now we have here a more realistic model. However, when we have here this derivative in a part of delay, what happens here is that we have a much more complicated type of problem, because now we call this equation here as a neutral type of equation. Always when we have the derivative in a part of the delay, we call this a neutral type of equation. And why this is so hard to deal? So it's hard to deal with this type of equation because when we have this neutral type, and for example, if you'd like to investigate it about some linearized stability or instability, what happens with the neutral is that when you linearize it, and when you see what you generated with that, like the semigroup that you generate, and if you'd like to understand better what's happening with this semigroup, what's happening is that for the neutral case, you can have infinite eigenvalues in the spectrum of your semigroup. So that's the main difficulty. So not so much for the linearized instability principle, because usually for linearized stability principle, you need some boundness, but from above. So this is not so hard to have when you have this type of spectrum with infinite eigenvalues. However, when you are trying to do something about instability, so you can have much more complications, because usually what we want is something from below, so some boundness, but from below for your semigroup. So this is much more harder when you have infinite eigenvalues in the spectrum. And the main thing is here is that, so Walter proved several properties for these equations, like existence, uniqueness of solutions, also continuous dependence on parameters, differentiability of this type of equations, of the solutions of these equations, and also the linearized instability principle. However, the linearized instability principle was completely open, and we decided to investigate that. So it was our main goal in this work, like how we could overcome this challenge about these eigenvalues in order to deal with this type of problem. So I will explain a little the techniques that we needed to apply here in order to have those results. So here is the problem, as we mentioned before, and the first step is to rewrite this equation in a more abstract form. So it's in this way here. As I mentioned before, this x of t is like not the partial derivative, but a function of the delay. So here we consider that's a function that takes the delay here in this interval, and it takes like xt plus theta. So, and then we have that. So here what we will show is that it's possible to rewrite in this abstract form, and we will see some conditions that I will explain later. And the main thing here is that in this abstract form, not only this model, but we can also fit other models in our case when we consider this type of equation here in the abstract form. So also we put here something in the engineer using, again, state-dependent delays. So here again, so since we would like to work to rewrite this equation in the abstract form, as we mentioned before, we will need here the evaluation maps. So here we have this evaluation map that you take this pair and then you take this phi and apply to t. So we have this evaluation map. And then we also consider the restriction of our evaluation map that is this one that we have here in C1. And then using those, the evaluation map and this other one, what we have is that if we define our G in this way here, using these compositions, and here what we have is that the projections concerning the first factor, and here is the projection concerning the second factor. So if we have our G in this way here, what we have is that we can rewrite now our equation in that abstract form. And then also we can ensure that our G satisfies all those assumptions that will be very important to us. So let's see which types of assumptions what we have here. So first, it's about continuity. So this, okay, our G is continuous. The second one is really important in our case, but because we need that for some calculations. And here we have no much problem with that, because if we see this G1 can be interpreted like the delay in the neutral term never vanishes, which means that, okay, in our case, there is no problem with that because we do not have choke between particles. But depends on the model, of course, you can have some troubles in this condition here. However, what it means is that, okay, our phi1 equal phi2 only in this interval ensures that when I apply the G for those functions, we have that they are equal. So it's something that direction. Here we have some local estimated for G that's expected, since we need the results concern existence and uniqueness of solution, differentiability of solutions. So we have a type of here local estimated. So, and more than that, we have this other assumption here, this G3, that's really important in our case. That's the linear extension of the derivative of the G. So what that means? So here we have that every derivative that here is defined in C1 times C1 has a linear extension. What that means is that now this linear extension will take from C times C. And this will be really important because using this hypothesis, you'll be able to construct a structure of manifolds. So here, and it's also important to mention that this condition also appears before, and it's called the almost Frechet differentiability, and it was introduced by many others like John Mallet Paré, Nussbaum, and others. And this property will ensure that this set that we have, if it's not empty, it is a continuously differential submanifold of Banach space. So it will be very important to have that. So we ensure that this set here has the structure of a manifold, okay? And here is the norm that we are considering in that case. And but one thing that's important to mention, okay, we have this structure of a manifold. However, we do not ensure that the set is invariant, which means that if we start in this set, you cannot ensure that you continue in this set. So here we need to define a subset of these sets in order to ensure the invariance, okay? So here we have a more estimated, so I will not enter very much in that because it's too technical. And here about some irregularity again. And here more estimated. So what is important here is that it was proven that our G now satisfies all those hypotheses, and it will be very important to us in order to have these results. So here, because we will, it's important to mention that all those hypotheses will be important to ensure like the existence, uniqueness, also differentiability, and we need those properties concerning our problem, okay, concerning our solution. So here is the problem that we have, and here is only to have the idea concerning about the definition of a solution. So a solution for us will be understood as a continuous differentiable function here that satisfies this equation for all time here in this interval, and also that we have this pair belongs to W, where W is an open subset of a C times C1. And then here is the set that now we need to define in order to have the closed subset of the manifold, and that this one will be the invariant. So here it will be very important to have this invariance. So here Hans-Otto Walter proved about this invariance. So if we start in that set, you continue in that set. So, but why we want that? Because here the strategy that we will use will be the invariance of Kohn. And that's why it's so important to have this invariant structure. And here again, we proved our results, everything for the abstract form, and then we apply that for the specific form in our case, in our context. So here what we have here this Banach space, and we assume that we can divide this space in a stable part and this unstable part. And what we have is that the semigroup that is generated that we have will satisfy this property concerning the unstable part and this property concerning the stable part. So we have those estimated. So here we proved first everything for the general case, like very abstract, and then we will see that it will fit in our case. This was one of the most difficult properties to prove, because as I mentioned before, the problem when we deal with neutral type of equation is that we can have infinite eigenvalues. And then it's really hard to have this type of boundness here from below. And that's the problem when you deal with this type of equations. However, here in our case, we could do some estimated to show that it's possible to have this type of estimated concerning the semigroup that we have from the linearization. Also here, the other property that comes very importantly in our case, it's concerning the semiflow. So our solution has the structure of semiflow. So it satisfies these three properties here. And we have that from the properties of our solution of our problem. And here, this one is really important because now it's a type of linearization, yeah? So here you have the nonlinear part minus, this is the linear part, and this is the difference between them. And what we ensure is that we can ensure that we have this small arrow that we have for all x that belongs to this ball here. We have that this is also very small, so we can do this linearization. So here, only to avoid to bring all the time this k that appears, we will work with an equivalent norm that will use this notation here. And in that case, we will consider our k equal 1. And then we have this other estimated in this case. And we will consider that now when we have an element of our space, since we saw that we can rewrite it in an unstable form plus the stable part. So we have that this norm here will be the maximum between the unstable part and the stable part. So now for C here, we define the cone. So here is the usual way that we have for the cone. So here all the elements in our space, and what we have is that this V belongs to the stable part, and U belongs to the unstable part, and we have this relation concerning here our unstable part. So now we have the result, that's the invariance of cone and expansion. So here we have our, like C belongs here, and our T1 in the same way that we have the property A3. And then what it has the following. So if we define our K in this way, so we have that's bigger than 1, and then there exists a delta such that we have that if X belongs to the cone and in the ball, so if we apply the T1 map, we have that the T1 map belongs to the cone. So we have here the invariance of cone. And more than that, we have the expansion of the unstable part. So here, this is the new unstable part of our T1 map. And if you see, it expands because we know that this Q is bigger than 1. So here only very quickly, I will only sketch the proof, but very quickly, only to give some ideas behind. So we take epsilon this way and the delta in order to satisfy the hypothesis A3. And okay, we use here some properties concerning the projection. So this is the projection concerning the stable part, and this is the projection related to unstable part. Then we apply in the T1 map the projection for the unstable part. And then we have this here. And then working on that, we have the other equality here. And now using the triangular inequality to the other side. And also here some estimated as we saw for the hypothesis A1. So we have this relation here. And then using the property concerning the cone, so we have this other relation here. So we have this inequality. Also here we have that for the stable parts, almost the same. So here we apply for the T1 map, the projection for stable parts. And then again, using the definition of our R, that's the difference between the nonlinear and the linear parts. What we have is that this equality here, and then working a little with those projections, we achieve this other part, and then using now the triangular inequality and the estimated concerning the projection, what we have is the following. And here is our hypothesis A3 that we have concerning this R. And then using that and the projections property, we have this other inequality concerning this other part. Now using again now the definition of our norm. So this is the elements in our space, and the norm 0, what we know is the maximum of the stable part and the unstable part. So which means these both projections here. And this one here, we know that is more or equal this amount here, because we saw just here, okay, this inequality. And also we have this other one here. So if this maximum is equal this one here, what we have is the following. So if we take our C is more or equal 1, okay, that is the one that we defined that appears in our cone. So what we have is the following. So here Since we are considering that the maximum is this one, so we have this inequality here. But since C is smaller or equal 1, we have this other inequality here. So, but if you see what we have is the following. So the T1 map belongs to the cone because it's exactly the property of to belong to the cone. Okay, so we have here, okay, I apply the T1 map and I am in the cone. So we have the invariance of cone in this case. However, we considered like the maximum equal this one. Now we need to consider the other possibility that the maximum is given by this other one here. And then considering that, so we have this inequality because of that, because now the maximum will be the other one. And now here, only working like a summing and subtracting things, we have this equality here. And now using the definition concerning epsilon that we took, so we have this other inequality. And this is exactly the inequality that we had in the beginning. So we have that this inequality we know from the beginning of our estimate. So if we see again, we proved that in this case, the T1 map again belongs to the cone. Okay, so here again, we have the invariance of cone. So, okay, we proved the invariance of cone, but also we needed to prove the expansion of the unstable part. And for that, it's again using this inequality that we had before, and now using the property concerning our, to belong to our cone, the property that X belongs here. So we have this other inequality. Now taking the choice of our epsilon, we have this other inequality here. So organizing things, we have this, and then since this is our Q, we have this inequality here. So we have the expansion of the unstable parts. So we proved everything for the abstract form. So now we can translate everything to our concrete case. Okay, so our concrete framework. So our E can be translated by the C0, our E2 can be translated by C2, and then the X can be translated by the invariant set that we saw before. So we can translate that, and we can have it for our specific case. We also discussed it before, how can we translate it, all those assumptions for our case. And it's not difficult to see that all those are satisfied in our case. But here, in order to have, okay, so we have now this invariance of cone and we have the expansion of the unstable part. However, here we need more things in order to prove our linearized instability principle. And in order to have that, we need a more one type of hypothesis. Because we need to ensure, okay, we have this XG2 star that's invariant, that's nice. However, again, we lose some structure of a manifold, and that's why we need another hypothesis in order to recover this structure of a manifold. And in order to do that, we need another type of hypothesis that now is the linear extension of the second derivative. So here we have the second derivative, and we have the linear extension to C times C. And using that, we can define now as M3, that's exactly our XG2 star, that's invariant, intersection of C3, that has the infrastructure of a manifold. And it will be very important to us to prove our results. So here, and also that's very nice here is that we have here this invariance because of that. But okay, we do not have that M3 is invariant, but we have that our solution will not escape from here because this is invariant. Okay, we escape from the manifold, but not from the set. And this is nice because we use that. So here is the main idea behind. So we have a ball and our solution. And if we apply the T1 map and our solution escape from the ball, what's happening is that our solution is unstable, okay? However, if our solution does not escape from the ball, we needed to apply again the T2 map. But what we know is that our solution continues in the cone because the cone is invariant. And also we know that it continues in that other set that's invariant. And more than that, from the property of the cone, we know that the unstable part, it expands. And in some moment, our solution needs to escape from the ball, because if you apply T3, T4, and many times there will be some moments that our solution escape from the ball because we are expanding the unstable part. So this is the main idea behind. So here only to mention that, it's exactly that. There will be some moments that our solution will escape from the ball. So, and then we have this linearized instability principle. Okay, so the second part, I will only bring very quickly ideas concerning more these state-dependent delays. And only to mention that we investigated this type of problems here. And again, with state-dependent delays. And here we had very complicated types of a problem because we needed to deal with infinite delays. And when we work with infinite delays, we needed to construct a phase space. And it's not that easy. It's very hard. So we need some properties concerning it. And also, we also worked in that case with X not being continuous, but also being regulated function. That means the lateral limits exists. So we need here to be a lot of careful because we have a composition of X, Rho, and then X again. So we need to ensure that this belongs to a good phase space, and this is well defined. Also, we applied our results for this equation, okay, using the definition of this A, that's the generator of zero semigroup, and then we apply it for that considering like state-dependent delays. So it was very nice work in that direction, but now I would like to mention that there are several open and developing problems in this field. So we have several works to think. For example, the model that I showed before, if we think about periodicity, bifurcation, all those are completely open questions, so are something to think. So there are many things in that direction. Also, I was mentioning that here we consider that space, that's the regulated functions, and it's not so easy to deal with that, and then maybe improve some results in that direction would be very nice, because okay, we needed to put some conditions here concerning this whole, but concerning about monotonicity, in order to ensure that these, when we have this composition, we can ensure that it's again in a good space and it makes sense. But maybe it's also possible to extend with more weaker conditions in that directions. And also investigated this type of problems using impulses. So there are many things in that direction that we can think that we could apply for those types of state-dependent delays. And also, for example, to mix PDEs and delays, even the constant delays, there are huge things to do, like many open problems in that directions. So how to put delay in the PDEs and how it works, like it's very complicated usually to have that. And it would be very nice to see how that will be in that case. So I worked with my co-authors in the Lamé equations, but in the constant delays, but it would be very nice to see this in other types of models and including more complicated types of delay equations. So that's it. Thank you very much for your attention.
Thank you very much for your nice talk. Very interesting. Okay, Any questions? Any comments? Remember that you can write on the chat also. Okay, no, we don't have questions, so thank you so much again.
Thank you. Thank you very much.
Okay, the next talk.
I have a question.
Okay, sorry. I didn't hear you. Okay.
Where is congratulations. One moment. One moment. Moment, please.
We are listening, just to tell.
I think it's a great talk. Congratulations. Well, I have a question. Do you have considered this type of question also with advanced? Do you study delay equation? Do you have considered equation with delay also, or not?
You mean like advanced, like in to the front, not to the past, you mean?
Yes, yes.
No, I haven't considered. It's also very, very nice type of equation, I think, with many applications, but we didn't consider these types, only from the past. Yeah.
So many years ago, I was involved in this type of problem. Can I share my string, and then I show you some article. Maybe if you are interested, I can send you. Yeah.
Oh, thank you very much. Okay.
Okay,
Yes,
one moment.
of course.
What moment, please? Yeah, I don't know what moment. Here. So, do you see?
It's coming.
Yeah.
Now, yeah.
Yeah. Here, for example, in 2005, we studied the instability of linear differential system with the state-dependent delay. Also here, we study differential equation with delayed and advanced arguments. I understood that you have worked with the delay depend of the state. That's right?
Yeah, exactly.
Okay.
Yeah.
Maybe you can find some here to apply your ideas. And here we have studied some about controllability of differential equation with delayed and advanced arguments. Also here.
Just to understand, you consider like mixed both, yes? Like
yes.
Okay.
Yes.
Okay.
And here, a spectral analysis of the semi-group associated to the mixed functional difference. Yes, it's a mixed equation. So if you have interest and here is another one, solution and constraint null controllability and here is recently we use C0 semi-group. Well, that I want to tell you is if you are interested, and so you can write me and I can send this article, and so maybe we can make some together. Okay.
Okay. Thank you very much. It would be very nice to receive then. Yeah. Thank you.
Okay, thank you for your question and comment, Professor Carmen. Okay, any other question? Okay, we have Torben. Let me.
Yes, I have a question concerning the strategy, how you solve the equations. Is there a possibility that you somehow can interpret the delay as some stochastic effect and then study stochastic equations in that framework?
Yeah, actually, you can investigate it like both, like there are many stochastic equations with delays. So you can have both. Actually, you cannot replace the stochastic process with delays, but you can put delay in the stochastic type of equations. The same happens for fractional. You can have like a fractional type of equations with delays, because the fractional will have will interpret it like the memory of the material, and the delay will have this time in between time, cause and effect. And the same about stochastic, because all these things about the probability, it is very important to have the stochastic part, you know. But of course, you can have the delay also together with the stochastic part. And also it's possible to have a more general than state-dependent delays. You can have also to have a delay that depends on other factors, including something together with probability.
Okay, thank you.
You're welcome.
Okay, thank you for the question. We have a question on the chat. The Lamin is asking about, hi, thank you for your response. I want to ask you about methods to solve second parts. And you do numerical parts?
I didn't make numerical parts, but it's possible to do numerical. And usually to solve explicitly some differential delay equations, what we have is that the step method. So you solve the solution, you solve the thing for one step, like for one interval, and then you can interact and you can solve for the other interval and so on. Because it's really important to know the initial condition in order to apply, to understand the solution for the next, and so on. So that's why. But we didn't apply for any numerical methods, but it's possible there are several numerical methods that we can work and to understand, including, for example, changing the delay. So you can see like you have some delay, and if you increase the delay, so what's happening with your solution? If you decrease what's happening, and if you come to the solution for the case without delays. So there are many things in that directions.
Okay, thank you. Lamin is here. Maybe do you want to do another question? No? Okay, thank you so much.
Okay, thank you. I think there is one question again in the chat, but I don't know if
really? Let me check. Yeah. You use a dynamical system as projective matrix? Thank you.
Okay, no, you're welcome. Yeah, we work a lot with dynamical systems, actually, with many types of properties in that directions. Usually it's nonlinear dynamical systems that we work. But we work a lot with dynamical systems in order to have these types of properties, the dynamic of solutions, and so on.
Mm-hmm. Okay. Any other question or comment?
Maybe I have a comment. Not. I don't have enough time to do the question to Jacqueline. Maybe I will email her later. But just Jacqueline, thank you very much for accepting the invitation of our organizers. Just an announcement that Professor Jacqueline Mesquita, who actually is president of the Brazilian Mathematical Society, also will be a speaker in the next conference, ISAAC-ICMAM Conference of Analysis in Developing Countries, which will be held the next week, exactly, on Friday. So I invite to all of you to participate in her talk. And also maybe another announcement related with the projects of women in mathematics that we have in ICMAM Latin America, right? Professor Jacqueline Mesquita with Yuriko Pitones and Pamela Harris. They are actually writing, right, a book about contributions of women in mathematics in Latin America. So we will share, of course, with you the book when published. So thank you very much, Jacqueline. Just short announcement.
Thank you very much, Duvan. Thank you.
Thank you, Duvan. Okay, thank you very much. The next speaker is here with us. Is the Professor Claudia Gareto. So it's my pleasure for me to introduce the Professor Claudia Gareto. Claudia Gareto is an outstanding Italian mathematician and a professor at Queen Mary University of London. She is also a visiting professor at Loughborough University, born in Asti, Italy. Gareto has an extensive academic background that spans multiple countries. She moved to Austria in 2002 to complete her PhD studies and spent 8 years at the University of Innsbruck. Following this, she joined Imperial College London as a junior research fellow. Currently at Queen Mary University of London, her research focuses on the analysis of hyperbolic equations and systems with multiplicities, an area she finds deeply fascinating. Today, she will talk about Schrödinger type equations with singular coefficients, and she will share with us a little about how she became interested in mathematics and at what point in her life she decided to become a mathematician. Please, Professor Claudia Gareto, you can start.
Okay, so now I can unmute myself. Thank you very much for the kind invitation. I'm really happy to be here. So, as part of my role at Queen Mary, the university where I am now, I'm also Equality, Diversity, and Inclusion Lead for the Faculty of Science and Engineering. And I run different activities to give visibility to minority groups in maths, and women, unfortunately, are still a minority group. So I'm actually really happy to be here today and to talk at this nice conference. So let me try to share my screen. Okay, let's do this. Share. Okay, here we go. So it should okay. No, let's do this. So share. Let's see if it works. Okay. Do you see it? Is that okay? Right?
Yes,
Yeah?
we can see.
Okay. Fine. Let me just put this down. Okay. So what I will talk today is actually a sort of a new project in collaboration with Alexander Arias Jr. from São Paulo University, Alessia Scanelli from Ferrara University, and Marco Cappiello from Torino University. So the title of this project is Schrödinger type equations with singular coefficients. So as you were saying in your introduction, I've been studying a lot of like PDEs, but in particular hyperbolic PDEs with multiplicities and hyperbolic systems with multiplicities. And in my career, I've also like focused on different methods like regularization methods to deal with PDEs with singular coefficients. So it was the first time with Alexander, Alessia, and Marco that I devoted attention to Schrödinger type equations. And this is one of the beauties of mathematics. So we come together from different fields, from different expertise, and we join forces to solve new and interesting problems. So this is the plan of the talk. So let's see. Okay, here. I will start with some introduction and why we are interested in this kind of problems. And as always, when we want to deal with some challenges, we need to have a deep understanding of the literature, or what is already known. And in this case, it means to understand what are the known results for Schrödinger type equations when the coefficients are regular. And with regular, I mean continuous in time, and usually I would say quite nice with respect to the space variable. So, for instance, smooth and bounded. Then at a certain point, we decide that we want to drop the assumption of regularity on the coefficients. So we wanted to allow coefficients that are non-continuous, and in general, we could even think about distributional coefficients. And therefore, we encounter many difficulties. For instance, how to define a notion of a meaningful solution, and therefore we will make use of a new notion of very weak solution that I will discuss later on. But let's start with the mathematics. Okay, so we want to investigate this kind of a Cauchy problem, where the operator S is a Schrödinger type operator. So which means in details that I have this part here, okay, which is the Schrödinger type. And then I will have lower order terms. So these are the terms of order 1, and this is the term of order 0. And in general, I want to deal with coefficients that depend on time and space. So why are we interested in this kind of problems? Because the Schrödinger equation is the fundamental equation in quantum mechanics. So clearly there is a strong physical motivation. And we know that this problem is well understood if we have a certain level of regularity, which basically means continuity in time and bounded and smooth behavior in X, so bounded also for all order of derivatives. So I will try now in the next couple of slides to have an overview of the classical results. So again, as many times when we deal with partial differential equations, we have a long list of mathematicians that have contributed to the analysis of these problems. So my review will probably not be really exhausting, but but I will mention the results that are more connected to what I will discuss later on. Okay, so we will see that well-posedness of the Cauchy problem is deeply related with the assumptions that we have on the coefficients, and could also be related to the dimension of the space where we are. So, for instance, we can get Sobolev well-posedness when all the coefficients Cj are real valued. And this is basically due to the fact that we will have a self-adjoint operator. It's a sort of a straightforward proof. The situation is much more delicate if we don't have this assumption on the coefficient Cj. So if we don't know that they are all real valued. So imagine that we have some imaginary part which is non-vanishing. Ichinoze in 1984 got interested in this kind of operators and prove a necessary condition. So in detail, it says that if the coefficients do not depend on the time variable, and here we have that a of t is identically equal to 1, then a necessary condition for well-posedness in H infinity, where H infinity is the intersection of all the Sobolev spaces, will be a certain logarithmic estimate on the imaginary part of the coefficient Cj. So this is the case where we have coefficients of order 1 that are not real valued, and we need, in order to have well-posedness, we need to have this kind of logarithmic estimate for the imaginary part. So the result of Ichinoze, which is a necessary condition, holds for Rn. However, if we work in space dimension 1, then this necessary condition becomes also sufficient. This is not true in general if we are in a space dimension which is bigger than 1. And there are some sufficient conditions, but usually they require not only hypotheses on Cj, but also hypotheses on the derivatives of Cj's, and these are quite technical. Okay, later on, in 1995, Kajitani and Baba, they also investigated this problem, so the well-posedness of this Cauchy problem. And this is a result that I will also mention later on in my talk. So let's assume that the coefficient AT is real valued and continuous. Let's take nice lower order terms, which means that the coefficients Cj and C0 are continuous in time and they are in B infinity with respect to x. And let's also assume that, again, they are not real valued, so we have the imaginary part of Cj, but this time we have a certain decay, which is a decay given in this way. So we can prove that the Cauchy problem is well posed, and the space where we will find well posedness has a certain relation with the order of decay. So if sigma is greater than 1, then we can get Sobolev well posedness of every order. We get well posed in H infinity if sigma is equal to 1, and if sigma is between 0 and 1, then we get well posed in Gevrey classes. So I've been working with the Gevrey classes quite a lot in the past, usually to prove well posedness of hyperbolic Cauchy problems with multiplicities. But Gevrey classes also appear in this case, and again, the Gevrey order is somehow connected with the properties of the coefficient. This is quite common. So, continuing this analysis of the well-posedness of this Cauchy problem, there have been more sophisticated results, for instance, by Cicognani and Reisig, and they obtain well-posedness in H infinity or in Gevrey classes, and under a certain assumption on the coefficient AT, and again under assumption of some special conditions that the lower the terms need to satisfy, and these are called the Levy conditions. Later on, Ascanelli, Cicognani, and Reisig also proved Gevrey well-posedness when there is a certain decay on the imaginary part of Cj. And in the case of a Gevrey index S, which is bigger than 1 over 1 minus sigma, under some exponential decay assumptions on the data. And very recently, there has been also work in the direction of Gelfand-Schilov spaces, and this was actually one of the results of my co-authors, so Alexander Arias Jr., Alessia Scanelli, and Marco Capiello. So this is a very brief overview of the classical theory. So now, what do we want to do? Okay, we want to allow more general coefficients. And for the sake of simplicity, because these kind of proofs are quite technical, and also our methods will require some regularization techniques, which makes things even more technical. So for the sake of simplicity, we will start by focusing on a Schrödinger type operator where the coefficients in the lower order terms have this shape. So basically it's the product of a function or a distribution in T and another function or distribution in X. And the keyword here is distribution. So I want to move from functions, regular functions, continuous functions, towards distribution. So I still need to have a certain level of regularity on the coefficient AT. So I need to know that it is a real valued function which is bounded, but it's also bounded away from 0, so it will never vanish. But then I can be quite singular on the choice of the other coefficients. So for instance, I will assume that the coefficients AJ are distribution with compact support, the compact support will be contained in a certain open interval within our time interval 0 capital T. And for the part in X, so for the coefficients in X, I want to take distributions with a certain properties at the level of the Fourier transform. So we have introduced these spaces of distribution here, h minus infinity 2, h minus infinity 0, and then similar spaces for the right-hand side and the initial data. And I will explain you in a moment what is the definition and also what is the motivation for introducing these kind of spaces. Before going into the details, let's just have a very introduction to why we want to do this. Okay, so first of all, if I really want to be general, right? So let's assume that I say, okay, I want coefficients that are distribution. It does not even make sense to write down the operator S. Because if I assume that AJ is a distribution and BJ is a distribution, then here I'm basically saying that I'm multiplying two distributions. And we all know that the space of distribution is only a space, not an algebra. So in general, I cannot multiply two distributions. So as soon as the word singular coefficients enters the picture, I have a problem of how to write down my operator and how to make sense of a solution. So this opens the door to all of this work that I have done in the last 10 years about dealing with singular coefficients, and which has led to introduction of this notion of very weak solution. And in a nutshell, basically means, okay, let's forget the operator S. Let's replace S with a family of regularized operators where we regularize the coefficients of the original operator S and we get nets of smooth functions out of this regularization. So let's have a look now at the precise definition of the spaces of distributions that we want to use. Okay, so this is the definition of the space H minus infinity I. So I'm taking temporal distribution that have this property at the level of the Fourier transform. So I compute the Fourier transform, I take derivatives up to the order I, and I have that these derivatives, they have like a polynomial growth. So I have a certain control on the derivatives of the Fourier transform. So, but why I'm doing this? Because I can get some extra regularity. Okay, so clearly I know that the Fourier transform will be of class Ci, and then the derivatives have at most a polynomial growth. But thinking already about the next step, and the next step basically means to regularize this distribution, it is quite interesting to see what happens when I do the convolution of a distribution U in this space with a mollifier. So what is a mollifier? A mollifier in general is a Schwarz function with integral 1, and I will define the corresponding regularizing net in this way. So this is a net of smooth function that will converge to delta when I compute the limit in the space of distribution. So now let's take U in one of these spaces and let's regularize it. So let's make the convolution with the mollifier phi epsilon. The net that I get out of this is a very nice net of smooth function. They are also bounded with bounded derivatives of every order, so it will be in B infinity. And then if I do all the computations, so basically here it's the same trick like, apply integration by parts, do your computation. So there will be some powers in epsilon appearing here, which are related to the order of the derivatives and the dimension of the space. but we can easily see that this quantity here will be bounded. So I will have a constant, and then I will have some negative power epsilon. So I get a net in B infinity, but also I get precise estimates on this net, which is clearly what I need. So we have introduced these spaces because after regularization with the modifier, we get coefficients that are in B infinity, and these are the kind of coefficients that we need to be able to apply the classical theory, for instance, to be able to apply the results by Cagitani and Baba. More precisely, we can have this very nice chain of inclusions. So here we have distribution with compact support. These are the distributions that are obtained by inverse Fourier transform of functions with polynomial growth. Then this is the inclusion that comes immediately out of the definition of these spaces. And all of these distributions will be contained in H minus infinity, which clearly is a subspace of the space of temporal distribution. All right, so now we have a setup. So we have our Cauchy problem. We have decided to take distributional coefficients, right, under the assumption that I showed you before. But now, what is our approach? So the approach, as I was saying before, is basically to regularize the operator S. So think about making this convolution with the modifier for all the coefficients that appear in the operator. Then we will have a net of nice regular operators that will converge to the original one when S tends to 0. At the level of the operator S epsilon, if we are careful in doing our regularization, and I will tell you more because we might need to have slightly different regularization methods according to the coefficient, right? So at the level of the operator S epsilon, if we have done things properly, then we will be able to apply the classical theory. So we know that a solution U epsilon will exist, but now we need to investigate the properties of this solution U epsilon, in particular, to see how the solution U epsilon depends on the parameter. We will need nice estimates in the right function spaces. So more precisely, this is how the operator, the regularized operator S epsilon will look like. If we have done our regularization in a suitable way, we will still have A epsilon to be a real valued continuous function that never vanishes. The coefficients here will be continuous with respect to time, and then the coefficient in X will be in B infinity. And in addition, we will also have this kind of decay of the imaginary part. So it's a polynomial, it's a decay of order minus sigma. We really need this kind of decay properties to be able to apply Cagitani-Baba result and therefore have well-posedness in H infinity. So this is the kind of setup that we want, okay? Now the point is to find the right regularization that will allow us to fulfill all of these bullet points. So in the next slides, I will go through this kind of regularization, and you will see that I will need a certain approach for the coefficient epsilon, and I will need slightly different approaches for the lower order terms. So of course, I also don't have to forget that we will have a right-hand side and we'll have initial data, and I will want to make sure that after regularization, I will have nets in H infinity. So if you have any questions, I haven't said that before, but if you have any question, please just feel free to ask. You can unmute yourself or put your question in the chat. Okay, so in detail, let's start with the coefficient in the principal part. So it is a distribution with compact support. I need to do the convolution, right? And I also need to make sure that a certain inequality will still hold. So I need to take a modifier which is between 0 and 1. When I do the convolution, okay, the convolution is defined on the real line, right? So I have to do a little bit of a trick, which is the one written here, where basically I extend the definition of the coefficient A from the interval 0t to the whole line, then I do the convolution, and then I do the restriction to 0 capital T. So this is quite a standard argument. But with this choice of the modifier, if you remember there was that bound from above and from below for the coefficient AT, it will still be true for A epsilon. I will just have here like a small change, which means that I have a 1/2 in front, but it doesn't change anything. So I might need maybe to reduce a little bit the interval where the parameter epsilon lives. So instead of going up to 1, maybe I just go up to a certain epsilon 0, but this doesn't change the complete picture. So this is fine. Okay, so this is what happens for the coefficient in the principal part. Now, let's look at the regularization of the coefficient in the lower order terms. So the T part, again, it's a similar argument. It's again convolution with the modifier. But what I see is that I get nice estimates on the absolute values of A, J, epsilon, T. So I get boundedness, but I also get here a negative power epsilon, which is really related to the structure basically of these coefficients AJ, so their orders as distribution. Now, let's not forget that we have also a part in X, so a coefficient in X. And let's repeat this regularization. I don't have to choose the same modifier for every coefficient, right? So I can choose a modifier if I want. But here we see why we needed to introduce these spaces of distribution. So why we needed like that assumption on the derivatives of the Fourier transform. Because this will allow us to have a decay here for the regularized net, which is of order -2 for the coefficient Bj's and of order 0 for the coefficient B0. Again, I do the regularization, so I get the decay that I want. But clearly, because I'm taking derivatives, I will have some negative power here of epsilon, where I see the order of the derivative, and I also see a certain constant which comes from the structure of my coefficient. It is very important in this kind of analysis to really have precise estimates. So sometimes we just write, okay, there exists a constant. Okay, it is not enough for us. So we really need to see how the constant depend on the coefficients in our equation, on the dimension of the space, and so on. And we really need to be precise on the dependence in epsilon. So finally, we need to regularize the right-hand side and the initial data. And again, if we choose right-hand side and initial data in these spaces, so h minus infinity n plus 1, then we will get a n plus 1 decay with respect to x, and we will get this for every order derivative. So as a consequence, we will have that these nets belong to every Sobolev space, and we will have precise estimates of the Sobolev norms. So if you are familiar with very weak solutions, I believe some people in the audience probably are, or in general, if you are familiar with the so-called theory of generalized functions or Colombo algebras, if you want, you will know that these kind of estimates are also known as moderate estimates. So via convolution, in a very natural way, we get estimates in epsilon that are moderate. I will say more in a little bit about this. Okay, so more precisely, we say that a net in C0t H infinity is H infinity moderate if for every m we have an estimate of the corresponding Sobolev norm of this type. So there exists some negative power epsilon such that we have this kind of an estimate. I can be very flexible, so I could replace the space Hn with a different space, okay? For instance, I could replace it with B infinity, and the moderateness will be defined in a similar way. So here we have the corresponding, if you want, norm, so in this case, semi-norm, but again, the behavior in epsilon is similar. So via convolution with modifier, we automatically get moderateness estimate in the right spaces that we want to deal with. So A epsilon, AJ epsilon, BJ epsilon are all B infinity moderate. And concerning instead the initial data and the right-hand side, they, after regularization, they will be H infinity. So we are now ready to give the proper definition of very weak solution. So before looking into this definition, let me just give you a little bit of a context. So the notion of very weak solution was introduced by Michael Różalski and myself in a paper in 2015, where we were looking at hyperbolic equations, so second-order hyperbolic equations with singular coefficients. And the idea is the one that I have given to you in this talk. So the idea has always been like, take the problem, regularize it, look at the family of the regularized solution. The notion of very weak solution is very flexible. So you can use it for basically every kind of PDE. But you define the notion of very weak solution which is suitable to your problem. So it could be that for hyperbolic equation, you need a very weak solution modeled on Gevrey classes. It could be that in a case like this one, for the Schrödinger type equation, then you need a very weak solution which is modeled on H infinity. How do you choose the space? Basically depends on the classical theory underlining the understanding of your problem in case of regular coefficients. So in this particular case, we say that the net U epsilon is a H infinity very weak solution for our Cauchy problem if there exists B infinity moderate regularization of the coefficients and H infinity moderate regularization of the right-hand side and the initial data, such that the regularized problem has a solution and the net of solution U epsilon is H infinity moderate. So it is not enough to say, okay, there exists a net of solution. We know that it will exist by the classical theory if we do the regularization right. We need to prove that this net has some specific properties with respect to the parameter epsilon. In other words, is H infinity moderate. So there will be now a theorem, right, which is our main statement, which basically says that yes, under suitable choice of the regularization method, a very weak solution for this Cauchy problem exists. So this is a very recent result. So it is contained in a paper which has been, it is on the archive and it has been recently accepted for publication. It is the first result written in collaboration with Alexander, Alessia, and Marco. And as I was saying at the beginning of my talk, it has been really an example of how people working in two different areas of mathematics can actually come together to solve a problem, and at the same time are enriched by this experience because they learn different areas of mathematics that were not their expertise before. So the Cauchy problem for the Schrödinger type operator, where we assume this assumption on the coefficients, so we have distributional coefficients with a certain particular behavior here, admits a very weak solution of H infinity type. So how does the proof look like? So it is very technical, so it is not the right moment to go into the details, but I would like to comment on a few facts and at least to give you the flavor, what it means to work in the context of very weak solution and to prove a theorem like this one. All right, so first of all, as I said before, very weak solutions were introduced for hyperbolic equations. There are now several results, and I believe we have quite a good understanding of hyperbolic system with singular coefficients, for instance, and second-order hyperbolic equations with singular coefficients. I know that when I was talking about the regularization, I always said, okay, let's take a mollifier phi epsilon. So that was like a simplification. So sometimes it is important to replace, it is actually necessary to replace epsilon with a general scale omega epsilon. So what does that mean? Basically, let's take a scale omega epsilon, which is converging to 0, which is bounded from below by a certain positive power epsilon, and let's define the corresponding mollifier. So why we do this? Because going through the proof, at a certain point, if we want to prove that our net of solution u epsilon is H infinity moderate, then actually we realize that epsilon is not enough. Maybe we have to choose an omega epsilon, which is like 1 over a logarithmic scale. So maybe we need like some really precise choice of the net. And we want to be able to have this extra flexibility. So for instance, in the specific case of the theorem that I mentioned before, we have that omega minus 1, okay, it's an iteration of logarithmic scales. So I need actually to iterate them 4 times. I know that it's basically not easy to see why now, because I would need to go through the proof. But just to give you an idea, you end up with estimates of this type. So the proof is mainly based on a certain change of variable that you implement so that your problem becomes slightly easier. And then you need to make use of some pseudo-differential operator methods. There is also like the Gordon inequality. The Gordon inequality entering the picture. You do like Sobolev estimates. And then at the end of the whole machinery, you end up with an estimate of the Sobolev norm of your solution u epsilon. An estimate which connects the solution with the right-hand side and the initial data, and then there is some constant, okay? So in the classical theory, I would say there exists a constant, which will depend in some way on the coefficients, the order of the Sobolev norm, and the dimension of the space. But in this case, we really need to be precise, and we need to understand what is the dependence of this constant on the regularizing parameter, so on the scale omega epsilon. It turns out that there are some exponential appearing there. And clearly this means that if in the end I want a moderate estimate, which means some epsilon to some negative power, then I need to balance this with some logarithmic scale. And I want to make sure that I can use the same logarithmic scale for every Sobolev norm, and that's why I need this sort of a choice of a net. Again, this is not new in the very weak solution community, so this is actually quite understandable, but clearly there are some technical difficulties. The paper goes through all the steps of the classical proof and makes sure that the dependence in epsilon is written in a very clear way. All right, so few questions. I've stated the theorem, so let's go back a moment. So this was the statement of the theorem. The statement of the theorem says there exists a very weak solution. And I know that people that usually work with Cauchy problems will be a little bit disappointed because we say that the Cauchy problem is well posed. So we should not only talk about existence, we should also talk about uniqueness of the solution. So there are a few questions. Here we go. And the first one is, what about uniqueness? So can we say that a very weak solution is unique? And the answer is not really, okay? So we need to be careful. So we can say that the solution is unique modulo negligible perturbation. So it means that if I perturb the regularization of the coefficient, adding some nets that go to zero in a very nice way, being negligible means that they can be estimated by any positive power epsilon. So if I do that perturbation at the level of the coefficients, then what I will get is a very weak solution, which is not very different from the previous one. So the difference between the two will be negligible. So negligible perturbation of the coefficients leads to H infinity negligible perturbations of the corresponding very weak solutions. So what does it mean to be negligible? It means this. So it means that I can estimate this Sobolev norm with any positive power epsilon. So it's going to zero, and it's going to zero in a very fast way. Okay, so this is how we handle uniqueness in the very weak solution context. Another very natural question is, what about consistency? So what happens when you know that your coefficients are nice, they are regular as they are supposed to be in the classical framework? So you already know that there exists a classical solution. Imagine that you regularize them and then you get a very weak solution. What is the relation between the two? Okay, so in this case, we need to be a little bit more specific in the choice of the mollifiers. So if we choose mollifiers that, in addition to have integral 1, have also all the moments vanishing, then we can prove that the very weak solution that we get will converge to the unique classical solution in the space C H infinity. And this convergence does not depend on the regularization. So I will always get as a limit, independently of the choice of the mollifiers that I do, I will always get in the limit the classical solution. And this is something that clearly we want to have because we want our theory to be consistent with the classical one. So in the very last few minutes, I would like to spend a few words about the future. Okay, so just to be precise, what it means that the moments are vanishing, it means that when I compute here this integral, so the integral of x alpha phi x, the x, this is equal to 0 for every alpha different from 0. So what's next? What about the future? Okay, so after we finished this paper where we proved the existence of very weak solution of Sobolev type, we decided to look into coefficients that are not the distribution with compact support. but only temper distribution. And it is possible to prove a similar results, but this time we will have a very weak solution of the Schwarz type, so rapidly decreasing very weak solution. And this is a paper which is on the archive, and it is currently submitted for publication. But what can we do? So what can be done, or at least attempt in the future? So the Schrödinger type operator that I've used in my talk is a special kind of p evolution operator with p equal to 2. But in general, one could write the operator that I have here on the slide for every real p bigger than 2. For instance, when p is equal to 3, this will recover some kind of a KDV operator. Not much is known about this kind of operator, so in the sense that there are results, but again, under assumption of regularity of the coefficients, so it could be interesting to try to see if the methods that we have employed for the Schrödinger type operator can be adapted and maybe generalized to p evolution operators with singular coefficients. And finally, what about including some nonlinearity? So clearly, after regularization, we are allowed to multiply any two coefficients that we want. So in principle, we should be able to deal with nonlinearity. At the moment, not much has been done in the context of very weak solution, and I believe this would be like an interesting line of research. So in this page, you see a few papers that are connected to my talk. So these are the papers, the two preprints that I've mentioned in my talk. This is the paper about very weak solution, and then some other work that I have done also in collaboration with my postdoc, Boris Abibtek, on hyperbolic system with singular coefficients. And that's the end. Thank you very much. I will stop sharing, and I'm happy to answer your talk. Amelie, I would like to add, because in the introduction, Karina was talking about also telling few things about my experience, right, as woman in mathematics. So giving visibility to women is really one of my priorities. And I remember when I was a student in Torino, Elena is in the audience. Ciao. When I was a student in Torino, I remember a lecturer teaching us algebra and the Noetherian ring. And the lecturer didn't mention that actually they were named in this way because of Emmy Noether. So I always assumed that all the mathematicians that were named in the class, they were like men, European, right? Probably with a beard. So I'm actually quite happy that now, at least in the UK, we do a lot of work to make sure that when we teach our students, we give a little bit of historical context to mathematics, and we make sure that the contribution of women to mathematics are recognized. So for instance, we have run a project with some PhD students here at Queen Mary on diversifying the maths curriculum. And we have discovered that, we all talk about the father of calculus, and the father of calculus are Newton and Leibniz. But actually, in the UK, there was also a mother of calculus, Mary Somerville, who did a lot of work to bring the calculus developed by Leibniz into the UK. And her work has been recognized only recently, when there were some historians of mathematics doing actually active research on the contribution of women to the development of mathematics into the UK. So I believe events like this one can really have an impact. So thank you very much for having me. Okay, maybe there were some questions in the chat. Let me have a look.
Yes.
Okay, can we use cutoff method to overcome a singularity? I guess it really depends a little bit on the kind of coefficients that you have, right? So the method that we are using here, because our focus is really like to be able to deal with a sort of a large family of equations, right? Then the convolution is the method which probably will give you more success because it can be, you don't really need so many assumptions, the coefficients, so you can apply just knowing that you have a distribution with compact support or you have a temporal distributions. But it could be that like with a specific choice of coefficient, maybe you can use different methods like cutoff, for instance. Yeah, so it's not a complete answer, but let's say that the focus for very weak solution is really to look at the possibility of dealing with the largest possible class of equations and coefficients. Any more
Okay.
questions?
He said, I think our work is very interesting. Can I contact you by email to know more?
Definitely. Definitely. I can write my email in the chat.
Thank you so much. Okay, any questions? Any comments or comments?
Thank
If
you.
not, thank you so much for agreeing to give a talk in this conference. Very nice talk.
Thank you very much also for accommodating the last minute change because unfortunately I had other commitments that I couldn't move. So thank
Yeah,
you
yeah.
very much and all the best to all of you.
Yes. Thank you for the Professor Paula Cerelleiras for accepting
Thank
to
you.
move. Also.
Exactly. Thank you, Paula. Thank you.
Okay, thank you all. Okay, so now we will start the break. Okay, we will return at 7 p.m. Central European Time. And so see you soon.
Bye bye, everyone.
Bye bye.
el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso. En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso. el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso.
Somos el cuerpo efímero, pero gracias a las matemáticas, nuestras ideas trascienden la mortalidad. Simbólicamente, las mujeres hemos sido relacionadas con el campo emocional, el cuerpo físico y la intuición, separado del hombre al que se le han atribuido características más intelectuales, relacionándolos con el mundo de las ideas y la toma de decisiones políticas con cabeza fría. Sin embargo, a lo largo de la historia, la humanidad se ha beneficiado de los hallazgos que miles de mujeres científicas han aportado a la sociedad. Por esto, desde el ISAAC-ICMAM Latin America, construimos una comunidad matemática inclusiva, respetuosa e inspiradora, que conecta a las mujeres matemáticas con entornos académicos internacionales, para visibilizar su trabajo y potenciar sus habilidades. Algunas de las mujeres líderes en matemáticas de nuestra institución son Karina Navarro González, Jessica González Hurtado, Yuriko Pitones, Marlisha Sandoval, Alexandra García Medina y Ruth Alejandra Torres Rubiano. Nos interesa aportar a un mundo más equitativo y justo, donde sin importar el género, las fronteras geográficas y económicas, todos y todas tengan la oportunidad de desarrollar una carrera exitosa en las ciencias matemáticas y contribuir al desarrollo humano y social. ICMAM Latin America, el lugar donde las matemáticas transforman el mundo.
Woman Mathematician, aprobado en febrero de 2024. El proyecto Visibility of Latin American Women Mathematician, aprobado en febrero de 2024 por el Committee for Women in Mathematics of the International Mathematical Union, busca visibilizar a mujeres matemáticas de Latinoamérica entre grupos de niñas y jóvenes de escuelas rurales, con el fin de concientizar que, sin importar fronteras, las mujeres matemáticas realizan grandes contribuciones en la ciencia y la industria. El objetivo es impulsar modelos femeninos a seguir en las carreras STEM y principalmente en matemáticas, para que las niñas de hoy y las mujeres del mañana tengan mayores posibilidades de alcanzar sus metas y aspiraciones, considerando como una posibilidad ser científicas.
Me acuerdo que en mi salón de clases de la primaria, al menos la mitad de los estudiantes éramos niñas. Luego en la secundaria, preparatoria y en la universidad, la proporción aumentó. De hecho, en mi generación de licenciadas en matemáticas, nos graduamos solo mujeres. Pero cuando pienso en el terreno de las ciencias y las matemáticas, me pregunto, ¿cuántas mujeres se desempeñan profesionalmente? Las cuentas no me cuadran. No recuerdo que en mi niñez me hayan acercado especialmente a las matemáticas. El entorno escolar no me preparó para indagar en el terreno académico y matemático. Si pienso seriamente, no encuentro los caminos ni las vías que me han traído hasta aquí. Tal vez me convertí en matemática por casualidad. Lo cierto es que fue y es una fortuna, porque si me transportara al contexto escolar en el que crecí, debería estar haciendo algo distinto. Lo que he dicho hasta ahora no es una queja ni un reclamo, sino una reflexión sobre lo que acontece en la escuela. El sesgo no solo ocurre en la formación académica, también en el entorno familiar y social. ¿Por qué pasa esto? Quizá porque se piensa que las matemáticas y las ciencias solo pueden ser practicadas por hombres, como los deportes, y entonces, por omisión, somos descartadas como futuras matemáticas y científicas. Nadie nos impulsa ni se ocupa de revelarnos que podríamos dedicarnos a las matemáticas, astronomía, física, química, medicina. Según un estudio de la Organización de las Naciones Unidas, en 14 países, la probabilidad de que las mujeres obtengan un grado de licenciatura es del 18%, 8% para un grado de maestría, y solo el 2% logra un título de doctora en alguna materia relacionada con la ciencia. La representación de mujeres en las carreras científicas es del 28%, frente al 72% de los hombres. ¿Qué tenemos que hacer para que estos números y nuestras realidades cambien? No tengo la respuesta, pero estoy segura de que la sociedad en todos sus niveles debe motivar el desarrollo científico en las niñas. Debemos hacerlo para no seguir desperdiciando el talento y las ganas de niñas y jóvenes. Así, en el futuro, podremos tener una ciencia vasta, gigante y más justa. Desde donde estamos, un grupo de mujeres matemáticas latinoamericanas buscamos impulsar y motivar a las niñas a ser científicas. El mensaje es claro y sencillo. Es importante conocer y reconocer a las mujeres matemáticas que se desempeñan profesionalmente hoy en día, que sean mentoras y modelos a seguir. Pero es más importante que nuestro mensaje llegue a todos los rincones de nuestro país. Cuando les preguntamos a las niñas ¿a cuántas mujeres científicas conocen?, algunas responden Marie Curie, y es que Marie Curie es nuestra heroína. Pero cuando les preguntamos ¿a cuántas mujeres matemáticas conocen?, hay un silencio prolongado y miradas buscando respuesta unas con las otras. Si hoy volvemos a hacer esta pregunta, las niñas con certeza responderán.
Hola, soy Yadira Valdivieso, soy matemática mexicana y hago teoría de representaciones.
Hola, ¿qué tal? Soy Verónica Redondo y actualmente trabajo también para el Senado de la República en la Secretaría Técnica de la Tesorería.
Hola, soy Ruth Alejandra Torres, matemática colombiana. Actualmente soy directora del programa Matemáticas de la Conrad Lorenz en Bogotá, Colombia.
Soy Rosibel Pacheco, matemática hondureña, presidenta de la Asociación Matemática de Honduras.
Soy Rita Jiménez Royand, matemática mexicana y soy investigadora en el área de topología algebraica.
Hola, ¿qué tal? Soy Raquel Perales, soy una matemática mexicana y mis áreas de investigación son la geometría riemanniana y el análisis geométrico.
Hola, soy Pati Jiménez, soy matemática mexicana. Trabajo en la Universidad Autónoma de Zacatecas.
Hola, me llamo Pamela Estefanía Harris. Nací en Guadalajara, Jalisco, México, y he vivido en Estados Unidos desde los 12 años. Soy matemática y mi investigación se enfoca en la combinatoria algebraica.
Soy Nancy Gelman, matemática de nacionalidad argentina y trabajo en Uruguay hace muchos años. Me dedico a los sistemas dinámicos y acciones de grupo.
Soy Marta Mendoza, soy una matemática mexicana. Mi área de estudio es la teoría algebraica de números, pero también me interesan la historia y la divulgación de las matemáticas.
Hola, soy Marta Álvarez, soy matemática que trabajo en Guanajuato.
Hola, soy María Isabel Cortés, matemática chilena y trabajo en las áreas de sistemas dinámicos y teoría de grupos.
Hola, soy María Chara, soy docente e investigadora de CONITEC en Argentina, la Universidad Nacional del Litoral, y me dedico a la teoría del código.
Soy Luz María García Ávila, matemática mexicana e investigadora en el área de teoría de conjuntos.
Hola, soy Leticia Brambila Paz, mexicana, trabajo en geometría algebraica, en particular en espacios módulos sobre haces vectoriales.
Soy Leslie Campa Raimundo, matemática mexicana. Soy investigadora en el área de mecánica celeste, particularmente en configuraciones centrales.
Soy Laura Rocío González Ramírez, matemática mexicana y soy investigadora en el área de matemáticas aplicadas a biología y medicina.
Hola, ¿qué tal? Mi nombre es Isabel Hernández. Soy matemática mexicana y mis áreas de investigación son el álgebra no asociativa y la teoría del.
Soy Gabriela Jerónimo, matemática argentina.
Trabajo como profesora e investigadora en la Universidad de Buenos Aires y en el CONICET en el área del álgebra computacional.
Soy Gabriela Araujo, soy matemática, trabajo en el Instituto de Matemáticas de la UNAM, en la unidad Juriquilla y me dedico a la comida.
Hola, soy Elizabeth Gasparín, brasileña que trabaja en Chile y me dedico a la investigación en geometría.
Hola, mi nombre es Edith Mireya Vargas García. Soy mexicana, profesora del Departamento de Matemáticas del ITAM. Mi área de especialidad es álgebra universal.
Hola, soy Diana Bueno, matemática colombiana y trabajo en teoría de códigos, es el área de las matemáticas que ayuda a entender el proceso de comunicación de manera fiable.
Hola, me llamo Claudia Reynoso de Cántara. Soy una matemática mexicana. Trabajo en la ciudad de Guanajuato, en México, y mi área de investigación es la teoría de foliaciones y la geometría algebraica.
Soy Carolina Úrsula Torres, matemática chilena, y soy investigadora en el área de análisis numérico.
Soy Carolina Mosquera, matemática argentina, docente en la Universidad de Buenos Aires e investigadora en el CONICET en el área de análisis armónico.
Olá, eu me chamo Andressa Gomes, sou brasileira e pesquisadora matemática. Atuo na área de equações expressivas e atualmente ocupo a posição de pós-doutorado na Universidade Federal do Piauí.
Soy Analía Silva, matemática argentina, trabajo en la UNSL y en el IMASEL y me dedico a las funciones diferenciales.
Hola, soy Amanda Montejano Cantorá, matemática mexicana. Soy investigadora en el área de teoría de números combinatoria, teoría de Ramsey y teoría extremal de gráficos.
Soy Elisa Wittgenstein, soy una matemática argentina, investigo en el área de geometría algebraica y aplicaciones, y desde fin de mes seré la presidenta de la Academia Nacional de Ciencias Exactas, Físicas y Naturales en mi país.
Hola a todas, soy Alexandra García, matemática y máster en Ciencias Actuariales y Financieras. Actualmente trabajo como actuaria regional en Allianz Trade, una compañía de seguros.
¿Ya estás grabando? ¿Sí? Sí. Bueno, como te decía, estamos haciendo el recuento de los hechos y la verdad es que este proyecto ha traído para mí mucha reflexión, mucha satisfacción, porque me ha permitido colaborar con muchas personas y con muchas instituciones. Quiero aprovechar para dar las gracias a todas las mujeres latinoamericanas que enviaron su video con un mensaje inspirador para las niñas y jóvenes. También quiero aprovechar para agradecer a todas las instituciones, a todo el personal administrativo y técnico, porque juntos hemos hecho que este proyecto sea una realidad. En particular, quiero agradecer a la Escuela Primaria Ignacio Zaragoza y a la Escuela Secundaria Técnica número 47 de la comunidad de Lobatos, Valparaíso, Zacatecas, a sus autoridades educativas, a los padres y madres de familia por sus autorizaciones y muy especialmente a las niñas y jóvenes por abrirnos las puertas de sus aulas, por permitirnos llevar este proyecto. Un video con un mensaje de muchas mujeres matemáticas, un mensaje inspirador y motivador. Hemos cumplido el objetivo. No fue difícil elegir el lugar donde llevaríamos este proyecto, porque yo también fui una de esas niñas que no consideraba las matemáticas como una profesión. Hoy, desde la posición en donde estoy, asumo mi rol y la responsabilidad que eso conlleva. Y estoy segura que, al igual que yo, muchas mujeres matemáticas seguiremos impulsando y promoviendo iniciativas para motivar la participación de más niñas y jóvenes en la ciencia y en las matemáticas.
No tengo la respuesta, pero estoy segura de que la sociedad en todos sus niveles debe motivar el desarrollo científico en las niñas. Debemos hacerlo.
Hemos sido amigos y colegas por mucho tiempo. Nuestro mayor logro, primero, poder formar un equipo de univallunos y segundo, poder establecer estas alianzas poderosas y que de alguna u otra forma visibilizan el talento matemático de Colombia en el mundo.
Mi nombre es Brian Grajales, soy egresado del programa de matemáticas de la Universidad del Valle y actualmente me encuentro haciendo una estancia postdoctoral en la Universidad de Campinas, en Brasil.
Mi nombre es Duan Cardona, soy egresado del programa académico de matemáticas de Univalle y actualmente soy investigador asociado del Centro de Análisis y Ecuaciones Diferenciales en Bélgica.
Con mi colega Duan tenemos nuestra organización ICMAM Latin America, que busca la conexión entre diferentes centros de investigación y entre diferentes investigadores jóvenes y expertos de todo el mundo a través de conferencias virtuales organizadas cada 2 años.
Nuestra empresa ICMAM Latinoamérica tiene 3 objetivos fundamentales. El primero, acortar la brecha que existe entre la interacción de jóvenes investigadores latinos con expertos internacionales. Segundo, publicar el trabajo científico de estos jóvenes. Y tercero, visibilizar el trabajo de las mujeres en las matemáticas.
Ser egresado de la Universidad del Valle es algo muy bonito y significa tener siempre un deber con la sociedad, estar siempre al servicio de la comunidad.
A un egresado de la Universidad del Valle lo caracteriza su integridad, su ética, su interdisciplinariedad, su capacidad de trabajo en equipo, de liderazgo y sobre todo de excelencia.
Soy egresado.
Soy Univalle. hemos sido amigos y colegas por mucho tiempo. Nuestro mayor logro, primero, poder formar un equipo de univallunos y segundo, poder establecer estas alianzas poderosas y que de alguna u otra forma visibilizan el talento matemático de Colombia en el mundo.
Mi nombre es Brian Grajales, soy egresado del programa de matemáticas de la Universidad del Valle y actualmente me encuentro haciendo una estancia postdoctoral en la Universidad de Campinas, en Brasil.
Mi nombre es Duan Cardona, soy egresado del programa académico de matemáticas de Univalle y actualmente soy investigador asociado del Centro de Análisis y Ecuaciones Diferenciales en Bélgica.
Con mi colega Duan tenemos nuestra organización ICMAM Latin America, que busca la conexión entre diferentes centros de investigación y entre diferentes investigadores jóvenes y expertos de todo el mundo a través de conferencias virtuales organizadas cada 2 años.
Nuestra empresa ICMAM Latin America tiene 3 objetivos fundamentales. El primero, acortar la brecha que existe entre la interacción de jóvenes investigadores latinos con expertos internacionales. Segundo, publicar el trabajo científico de estos jóvenes. Y tercero, visibilizar el trabajo de las mujeres en las matemáticas.
Okay, so hello everyone, and welcome to this exclusive interview with a true luminary in the world of mathematics. We are absolutely honored to have with us today a distinguished mathematician, a Fields Medalist, and a professor at one of the most prestigious universities in the world, Princeton University. His groundbreaking work has had a profound impact on the fields of mathematics, and he continues to inspire mathematicians and researchers worldwide. Please join me in extending a warm welcome to Professor Charles Pfefferman.
So, well, thank you for the very kind introduction.
Thank you, Professor Pfefferman. So, Professor, please, in a few words, could you introduce yourself and describe your current role at the Department of Mathematics at Princeton University?
Oh, sure. So, I am Charlie Pfefferman. I'm a math professor. In the past, I've had various administrative roles, but at the moment, My relationship with the math department at Princeton is very simple. I teach and do research, period. It is a pleasure to be free for the moment of administrative responsibilities.
Okay, so great. So I would like to ask you, Professor, how did your early interest in mathematics develop?
Oh, okay. So maybe I describe how it started, and then just a brief comments on the last 50 or 60 years. When I was a little child, I was interested in children's science, how rockets work and things like that. I wasn't content with children's explanations. And so I took a physics book out of our local public library. I couldn't understand a word. My father explained to me when I was a little kid, no, of course you can't understand this. It uses math that you don't know. Oh, well, can I study math? Okay, what grade are you in? I was in the 3rd grade. Okay, fine. I'll go and buy you a 3rd grade math textbook. And so I read it quickly, and I said, okay, can I please have a 4th grade math textbook? Oh, come on, you can't have read it in whatever, a day or two. Yes, I did. My father asked me a few questions and decided that I merited getting the 4th grade math textbook and so on. And I've never looked back from that point. Math fascinated me. I became addicted to it. Physics is very nice, but it fell by the wayside. And I've been then very, very fortunate. I lived within driving distance of a good university, the University of Maryland. I was introduced by my parents to a professor in their math department. He in turn introduced me to other professors. The University of Maryland mentored me beautifully. It was a big state school, but it felt like an army of private tutors for me. When it came time for me to go to graduate school, I went off to Princeton. I would say I was somewhat lost for my first year, but my second year, Eli Stein returned from a year's leave and gave a wonderful grad course. And I decided, okay, I had to work with him, and I did. It worked out very, very well.
Wow, amazing. Maybe I would like to ask Professor Pfefferman, could you share your experience of working under the supervision of Eli Stein, and if you have a favorite mathematical result, a product of this collaboration?
Oh, sure. So, all right, working with Eli Stein is amazing. So there are good teachers and there are great teachers, and then there is Eli. He was simply the best teacher of I believe of advanced math in the whole world by far. And so one thing that he did, one intangible thing, is that he conveyed a spirit of optimism. And well, math is hard, and if you want to succeed in math, you had better have a lot of courage and a lot of optimism. And Eli conveyed that optimism. I remember once he and I had to use some inequality of Hardy and Littlewood. It was a little obscure. Neither of us knew the proof. We went to the library. This was, of course, long before the internet. We went to the library, and the complete works of Hardy had been checked out. And so I thought, well, checkmate, we have to wait until it comes back. But Eli immediately said, never mind, if Hardy and Littlewood could prove it, we can prove it too. And we went back to his office, and in a couple of hours, we found a proof. And that spirit that you can do it, Eli conveyed that. And I mean, there were many, many other things that he conveyed. He has a wonderful style of explaining math in which almost all of the effort of explanation goes into finding the right point of view and explaining the essence of the problem. And at the very end of the explanation, in a few minutes, the
moralito de que el día que estuviste en Urumita y no quisiste hacer parranda, te fuiste de mañanita, sería de la misma rabia. Te fuiste de mañanita, sería de la misma rabia. ¡Upa! ¡Ay, hombre! En mi nota soy extenso, a mí nadie me corrige. En mi nota soy extenso, a mí nadie me corrige. Para tocar con Lorenzo, mañana sábado día de la Virgen. Para tocar con Lorenzo, mañana sábado día de la Virgen. Me lleva él o me lo llevo yo, pa' que se acabe la vaina. Me lleva él o me lo llevo yo, pa' que se acabe la vaina. Ay, Morales a mí no me lleva, porque no me da la gana. Moralito a mí no me lleva, porque no me da la gana. ¡Upa! ¿Qué cultura va a tener un indio en Yumeca como Lorenzo Morales? ¿Qué cultura va a tener si nació en los Cardonales? ¿Qué cultura va a tener si nació en los Cardonales? ¡Ay! ¡Upa! Morales mienta a mi mamá solamente pa' ofender. Morales mienta a mi mamá solamente pa' ofender. Para que él también se ofenda, ahora le miento la de él. Para que él también se ofenda, ahora le miento la de él. Me lleva él o me lo llevo yo, pa' que se acabe la vaina. Me lleva él o me lo llevo yo, pa' que se
Okay. Hello again, everyone. We will continue with our program, scientific program. And as we come to the close of the first day of the ISAAC-ICMAM Women in Mathematics Conference 2024, I want to extend my heartfelt thanks to all our speakers, poster presenters, and participants for their engaging contributions. We officially starting with the poster session. So the first poster is Diksha Gupta from Indian Institute of Technology, Delhi, India. The poster is about existence of high energy positive solutions for a class of elliptic equations in the hyperbolic space. So thank you so much, and you can start, please.
Okay. Hi. I hope I'm audible and my screen is visible too.
Yeah.
Okay. Hello everyone. I am Diksha, a final year PhD student at Indian Institute of Technology, Delhi. I would like to thank the organizers for giving me this opportunity to speak here. So I'll present one of my works I have done in the initial years of my PhD. So I have been working upon elliptic equations that enjoy some variational structures, but in a non-Euclidean space called the hyperbolic space. So such type of elliptic equations generally occur in differential geometry, and one of the very famous problems is the Yamabe problem. That is one of the major motivations to study critical exponent problems, and I have been studying them, as I said, in the hyperbolic space. So a little bit about the hyperbolic space. So hyperbolic space originated when mathematicians were trying to prove the Euclid's fifth postulate from the other four, but they were failing again and again, only to realize that there exists a space in which the fifth postulate fails while the others hold. So I have given a picture here. So there are various models to view hyperbolic space, one of them being the Poincaré disk models, where the geodesics are these arcs perpendicular to the ball, and this ball is B01 Euclidean ball. So you can see that given a point P and a line which does not pass through P, there exists more than one line parallel to the given line and passing through P. So the Euclid's postulate is failing. Moreover, we can realize this ball as a Riemannian manifold with this metric, and 2 upon 1 minus mod x square square times the Euclidean distance. Moreover, you see that the boundary of the ball will act as infinity for the space, for the hyperbolic space. Now, hyperbolic space is very rich in the sense that it retains some properties of the Euclidean space and also has some properties of its own. So, from the point of view of PD, the very famous Poincaré-Sobolev inequality, which does not hold in the entire space Rn, it does hold in the hyperbolic space, and this is more or less the property of negatively curvatured spaces, or more generally I could say Cartan-Hadamard manifolds. So, and this quantity n minus 1 square by 4 that appears here is the bottom of the spectrum of the negative of Laplace-Beltrami operator in the hyperbolic space. So the motivations to study elliptic equations came from the works of Sandeep and Manchini when they were trying to study the positive extremals related to the Hardy-Sobolev-Mazur inequality. And while the HSM inequality has a singularity. They lifted this equation to the hyperbolic space with the suitable transformation and found this equivalent equation. And motivated by this, I have been studying. Now, this equation is symmetric in the hyperbolic space. Using this, I have motivated by this. I have been studying non-scalar, non-radial perturbations of this equation. Moreover, firstly, I studied this equation with potential AX, and this AX is, I have assumed, non-radial and has some asymptotic condition that it at infinity it is going to 1 and also enjoys some growth condition. I have studied this using a variational structure. So we'll look at the critical points of the associated energy functional. Moreover, the major difficulties while studying such problems are that uh, it that firstly it is not symmetric, so we cannot transform it to the ODE and follow the techniques of Sandeep and Manchini. Moreover, there is a loss of compactness in the sense that the Sobolev space H1Bn is not compactly embedded in the L2 star space, and moreover, in the hyperbolic space, it is not even embedded for the subcritical range, that is P between 2 and 2 star being 2n upon n minus 2. So also we have not assumed that AX is going to 1 from above or below. So we cannot really compare the energies of the limiting problem and our perturb problem. So to look at ground state solutions were a bit difficult. So we found that the Bahari-Lee's min-max method was the most suitable to study this. However, okay, so firstly I'll just state the main result. So we established that if AX satisfies that asymptotic and growth condition as mentioned A1 and A2, then we established the existence of uh, a positive solution for lambda in this particular range. And the major theorem or method we used was to characterize the Pallas-Mail sequences, that if UN is a Pallas-Mail sequence associated Pallas-Mail sequence of a functional being, that uh, I lambda, if I'm talking about a Pallas-Mail sequence associated with I lambda, then it means that I lambda UN is bounded and I dash I lambda dash UN, meaning its Freche derivative, is going to 0 in the dual of the space. So I've characterized those Pallas-Mail sequences, that if UN is a Pallas-Mail sequence associated with a problem, then it has to be the sum of its weak limit U bar and some finite profiles, which are basically the solutions of the limiting problem studied by Sandeep and Manchini. And then using that, we found the existence of a solution, and the main lemma was this energy estimate, which involves computing the energy of convex combination of two bubbles being the uh, solutions up to hyperbolic translation. Hyperbolic translation is analogous of Euclidean translation. However, it is much more non-linear. And we found that this energy will be strictly less than the second level of the breakage of the Pallas-Mail, that the energy of the hyperbolic bubble. But this lemma, this energy estimate was very delicately handled because firstly, we don't have an explicit expression for the hyperbolic bubble as it is there in the Euclidean case, the Aubin-Talenti bubble we call it. But still we were able to and also the hyperbolic volume grows exponentially. To be precise, the radial transformation is sine hyperbolic to the power n minus 1. However, in the Euclidean, it grows exponentially. It grows polynomially. But again, we were able to handle the integrals involving the hyperbolic bubbles because Sandeep and Manchini also established an asymptotic estimate that they showed that the solution will decay like this. So we found that this volume growth, e raised to power n minus 1 r, is not more than this decay. So we were able to handle this, and we were also inspired by the works of Vegali and Glodo, who uh, uh, performed these estimates for the Auburn-Talenti bubbles. So we divided into different subregions and used the precise asymptotic estimate of this hyperbolic bubbles. Then we used the min-max method to establish this existence result, and we found this critical level uh, which corresponds to a critical point, and hence the solution. Also, this critical level then lies between the first and second level of the Paris-Mel breakage, and that is why we are calling it a high energy solution. And yeah, and we use some center of mass type function and topological degree argument to find that this level will be greater than S1 lambda, while this energy estimate we established here made sure that it will be below the second level. So yeah, this is the Bahari Lee's work, first reference, and second is my published work with my PhD supervisors, Professor Ganguly and Professor Srinath. And this is the work by Sandeep and Manchini, where they studied this limiting problem. So yes, that is all. Thank you.
Thank you so much. Okay. Does anyone have some questions or comments? Please, for questions, you can raise your virtual hand. The technical support. Sorry, my camera was closed. The technical support will activate your microphone, or you can write on the chat. Eder Alfaro said, congratulations, Diksha, I think.
Diksha, yes.
Okay, thank you, Diksha.
Yeah.
Maybe.
Okay.
Maybe I have a question.
Yeah.
Okay, Diksha, congratulations for your very, very, very nice presentation.
Thank you.
Sometimes it's difficult, right, to explain in this very nice way in a poster, right? And you did very nice. I have a question about the constant in your Poincare-Soulep inequality. Do you have information if this constant is a sharp constant or?
Yeah. It is the optimal constant. Yes, Sandeep Manchini actually have completely studied this equation, the existence, non-existence, P in the subcritical range, critical range, everything. So it is the sharp constant, and this inequality can be achieved if you know the Hardy-Sobolev-Mazur inequality. So it can be achieved using that only by a suitable transformation. Yeah, you can look at this very beautiful paper. It has been very well written. So yeah.
Wow, very interesting. And
Yes.
maybe last question, right?
Sure.
If you can share maybe some open problems that you are considering related with this work.
Okay, so right now, so my main goal was to study this problem with P in the critical range, which is 2n upon n minus 2. But we saw that there is a gap in the literature, so we decided to study this subcritical as well. So I have studied this completely in the critical now. That was my last paper. Then I wanted to see the fractional Laplacian. Now the equations involving the fractional Laplacian, but in the hyperbolic space only. However, I'm facing very much difficulty there because I don't even know a proper definition of fractional Laplacian in the hyperbolic space. So there are very, very few papers, or say there's a very minimal literature that I have. So I am trying to look at the same equation, but with the fractional Laplacian. Moreover, I want to work right hand with not this right hand side, but non-local right hand side also, which we call it as the co-card in the Euclidean case. So I have done one work with the Laplacian and the co-card, but I want to move to now a non-local operator and a non-local right-hand side. So that is one of the open problems. Not much has been done there. I hope this answers your query.
Wow, thank you very much. Impressive, thank you.
Okay, thank you, Duan, for your question. Thank you so much for the nice presentation. And now we have the next poster presenter. The next poster presenter is the Umama Heshwari. Sorry for my bad pronunciation. With the qualitative uncertainty principle for the linear canonical Dankel transform. So please go ahead.
Hello, is it audible?
Yes, I can.
Okay. Hello, everyone. I'm Uma Maheshwari, a research scholar at SRM University, AP. The title of the poster is Uncertainty Principle Associated with the Linear Canonical Dankel Transform. Mainly, I'm going to talk about two things. First, linear canonical Dankel transform and some related uncertainty principle, especially Hardy and Miyachi uncertainty principle. First, we need to know about what is linear canonical Dankel transform. For that, we need some basics. Here, I gave some notations. Initially, we introduced the some weighted measure. By associating this measure, we will introduce the LP space. This is nothing but weighted LP space. This is the collection of measurable function, and the function should be Pth integrable. Then, based on these notation, we introduce the Dunkel transform. This Dunkel transform is nothing but generalization of Fourier transform. For a L1 integral function, we define the Fourier transform. Suppose the Fourier transform of f is nothing but integration over R, f of x. There we have the kernel e raised to minus x dot psi dx. Instead of that kernel, here we have some different kernel. It is called ek of minus I lambda comma x. This kernel is defined in terms of normalized spherical function. It is the most generalized integral transform, generalized version of the integral transform. By using this Dunkel transform and the 2x2 matrix parameter, the author Gassoni introduced the new integral transform called linear canonical Dunkel transform. If f is a L1 integrable function and the linear canonical Dunkel transform is denoted like this, it is equal to integration over R f of x, this one. Here the major difference between the Dunkel transform and the linear canonical Dunkel transform is the kernel. Up to this is the Dunkel kernel with this extra factor. We call it as kernel for the linear canonical Dunkel transform. So, in the classical setting, what are the properties hold true for the Fourier transform? The same properties will true for here also. Suppose f is a L1 integrable function and transform of the function also L1, then we can talk about the inverse, right? So, inverse transform of the DKM is nothing but f, and Plancherel formula also holds here. If f is L1 and L2 integral function, then transform of the function also belonging to square integrable, and it is moreover it is preserving the norm also. So, these are the theory for the linear canonical Dunkel transform. Next, uncertainty principle. Initially in 1927, Heisenberg introduced this principle. It stated that it is impossible to determine the precise position and speed of a particle simultaneously. Later, this principle restated in the Fourier transform setting in this way. Like a non-zero function and its Fourier transform cannot both be sharply localized, which means we can understand through this example. Here we took the function on the interval -1, it takes the value 1/2. Remaining it is 0. We can find the corresponding Fourier transform of the function. The Fourier transform of the function graph is looking like this. Here, this function having support -1, but this Fourier transform of the function graph having infinite support. So we cannot localize function and its Fourier transform. That is the meaning of the uncertainty principle in the setting of Fourier transform. Here we establish the Hardy uncertainty principle. Initially, Hardy introduced the uncertainty principle for the classical setting, but here we extend this uncertainty principle for the linear canonical Dunkel setting. This uncertainty principle basically tells that nature of the function. Here, suppose f is a measurable function and the f of lambda and transform of the function is bounded by the Gaussian function. Then, based on this constant CST, based on this constant condition, we have the different kind of function. The first is, suppose st greater than 1 divided by 4b square, we have the function, this function is identically 0. Based on the second condition, we have the function equal to some Gaussian type function with this constant. The third condition as well, if st less than 1 by 4b square, we can get many function like this. Later, by changing some assumption, Miyachi introduced the uncertainty principle. By using that uncertainty principle, here we extended my setting, like a linear canonical Dunkel setting. Here f is a measurable function and e raised to sx square f belongs to LP plus LQ. Then with this assumption, then this uncertainty also talking about the nature of the function. What are the results hold true in the Hardy uncertainty principle? The same things will true here also. Only is the difference is assumption. These are the main result for this presentation. And these are some reference. That's it. Thank you.
Thank you so much for the nice talk. Okay, so any questions or comments? Okay, maybe I have one question. Do you know maybe do you know some applications of this transform?
Applications of this transform, image processing, like signal analysis, there this transform will play a role, basically.
Okay, nice, very nice.
Okay.
Any question? Let me check the chat.
Maybe I have a curiosity. Thank you for your very nice presentation. If I understand well, right, all the results that you shared with us were in dimension 1, right? One dimensional. Have you considered the extension to the, let's say, to the high dimensional case? The high dimensional case?
Yeah,
Or do you know if there is something in literature?
We can discuss this uncertainty principle for the higher dimensional case also.
Okay.
It won't be that much difference. Some little difference will be there. So.
Okay. It's straightforward, you mean, right? Okay. It was a very clear presentation. Thank you.
Okay.
Thank you so much, Duan, for your question. Okay, we have a question on the chat. Curious question. How is your name? Okay, about your name pronounced. Excuse my ignorance.
Shall I pronounce my name or what?
Yeah.
Yes, he's curious about it.
Yeah.
Uma Mageshwari. Uma Mageshwari.
Okay. Thank you so much.
Okay.
Okay. Andrea?
Yes. So our third presenter, sorry, is Atulia P. from Department of Mathematics. Sorry if I mispronounce your name. From SRM University, India, presenting your poster title, A Generalized Differential Difference Operator. Thank you. You can share your screen.
Am I audible?
I can hear you. Yes, I can hear you.
Okay.
Yeah.
Thank you. I will share the screen.
Yes. Thank you very much.
Okay, good evening. I'm Adilya from SRM University. And thank you for giving the opportunity to present my work in this conference. The title of the poster is A Generalized Differential Difference Operator. As per the title itself, we are defining a differential operator related to the transform linear canonical Dengel transform, which is a generalization of the Dengel transform. As you already seen that the Dengel transform is a generalization of the Fourier transform. So here we are developing a differential operator called the linear canonical Dengel differential difference operator. And corresponding to this operator, we are studying some properties of this operator. And then we came to the Laplacian related to this operator. Then we are discussing some harmonic functions related to this operator. And as a application, we just include the heat equation related to the Laplacian related to this transform. So before going to defining the Dengel operator, we need some preliminaries. So I start with the reflection map. If we have a non-zero vector alpha in Rn, we define the reflection map by this formula. Actually, this formula tells us that if we have a vector on Rn, if this vector is an alpha perp, the reflection map will serve as an identity map and it will send alpha to minus alpha. The finite subset of Rn, which is called root system, if it satisfies two conditions. First one is mainly the elements of this root system, we call it as root. So if one root is there, then the scalar multiples of the root, it's only alpha or minus alpha should be there in the root system. And we can generate a reflection map with respect to this root called sigma alpha. This root system should be invariant with respect to this reflection map. If a finite subset satisfies these two property, then we call it as a root system. This is a particular example of a root system generated by 8 vectors. And we can partition this root system into positive root system and negative root system. This is not unique. If we choose a vector B in Rn, which does not belongs to any of these hyperplane, this alpha perp, for where alpha belongs to the root system. So this B can make a non-zero inner product with each root. If we collect the roots which are making positive inner product with this B, and we call it as a positive root system, and the other vectors are negative root system. The group generated by these reflections, where alpha belongs to R, we call this group as a reflection group. If we took along these reflections, it won't make a group structure. So we are taking a group which is generated by this reflection, and we call it as a reflection group. Here our root system is finite, so that the reflection group will also finite. And then the function k defined on the root system is called a multiplicity function if it is invariant under the group action. Normally we can define this k to c also, but we are restricting particularly for the non-negative real values. And with respect to this multiplicity function k, we define a weight over Rn by this formula. And this weight is also invariant under the reflection group. And with respect to this weight, we can define the Lebesgue space. And now we have the ingredient to define the operator. The operator is called a Dengel differential difference operator. And it is denoted by T psi. And the first part of this operator is partial differential operator. And along with this, we have a reflection part also. So if we see here our k is identically 0, then we have the normal partial differential. And here also in the weight function also, if our k becomes 0, we have the weight 1. So we will end up with the weight, instead of weighted Lebesgue space, we will come to the normal Lebesgue space, and whole theory will land to the Fourier setting. And if we solve this in this eigenvalue problem, we will end up with a function called Ek. We call it as a Dangle kernel. How the partial derivative of the differential operator behave with the exponential function. Similarly, we have here also Dangle differential operator and the Dangle kernel. And associated with this operator, we can define a Laplacian, which is denoted by k, because k have a significant role there. And t summation I equal to 1 to n t ei square. And the normal Euclidean setting, how we are defining the Laplacian, same way here also it is defined. And the functions which are satisfying Laplacian k u equal to 0, we call it as k harmonic function. So associated with this differential operator, there is a transform called a Dangle transform, where this kernel Ek will serve as the kernel for this transform. It is defined by dk f of y equal to ck into integral over Rn f of x ek minus ix y wk of x dx. And this ck is a normalizing constant for the Planger's identity. And what all things are proved in the Fourier setting, it can be seen in Dangle setting also. We have, and associated with this transform, we can talk the translation also. Normally in the Fourier setting, we have the translation f of x minus y. But here, that translation won't work here. So we are defining a translation with the property that if we take the translated functions transform, we have the property that kernel multiplied with the transform of the function. So if we pull it back, we have the inversion formula. By using that property here, we define the Dangle translation. And it corresponds to this translation, the convolution structure is also there. And now we can move to the more general context called the linear canonical Dangle transform. In 2017, Gazzoni et al. Defined the linear canonical Dangle transform. And with respect to 3 independent parameters, where AD minus BC equal to 1. These A, B, C, D are the parameters. For B not equal to 0, he defined the transform like this. And for the case of B equal to 0, we have this formula. And we are more interested on B not equal to 0, so we have an integral representation. And the kernel for this integral transform is Dangle kernel along with an exponential factor. And this transform also satisfies the similar property of the linear canonic Dangle transform also. And now onwards, our contribution to this area. And we define a generalized translation along with this transform. To define more property of the translation, we need a space called AK, where the function and the transform of the function should belongs to L1 space. So this formula will behave very well. Normally, the transform of the translated function is transform of the function into kernel will be there. But if we pull it back, one more kernel will come there. But here we have an exponential factor because we are in a linear canonical setting. And we can represent this translation in accordance with the Dangle translation also. It is given by this formula. So what all representations are there in Dangle translation, we can adapt that representation here also in the generalized setting. And by using this translation, we can construct the convolution by this formula. The basic property of the convolution is if we take the transform of the convolution product, it will be the product of the transform of functions. And here, one more additional part is there, because we are treating here as exponential kernel is also there in our kernel. So now we can introduce our differential operator. Normally, we will introduce a operator corresponds to transform by the kernel will serve as a eigenvalue for the operator. So here we define this operator by the property that the kernel EKM will be the eigenvalue for this operator. So we got it as T xi minus I d by b q xi, where T xi is the Dangle operator and this q xi is a multiplication term. So the one property of this operator is if we have a different values of k, a, b, c, and d, we can convert this transform as Fourier transform, linear canonical Fourier transform, fractional transform, Dangle transform, and linear canonical Dangle transform, fractional Dangle transform. So according to these transform, we derive a differential operator related to this transform by this single formula. And next we define the Laplacian corresponds to this differential operator by taking the normal sense, that is IM square. And we call the functions which are the delta km u equal to 0, we call it as km harmonic function. And we list out some properties of this differential operator. For a fixed matrix M, if we choose any vectors I1 and Psi2, these operators will commute each other. And we have a skew symmetric property, and we have a product formula, and T psi M leaves CC infinity and S of R in invariant spaces. And this operator will behave well with the linear canonical Dengel transform. And these operators will commute with the translation also. So next one is our main result. It's a mean value property associated with this Laplacian. In the classical setting also, we know we have a mean value property related to our Laplacian. And here also related to our Laplacian, a function is called Km harmonic function if and only if it satisfies the corresponding mean value property. And then as an application, we included a heat equation associated with this Laplacian. The usual heat equation, we are just imposing instead of the usual Laplacian with our Laplacian. And then we find out the solution as the generalized convolution product of f with ft m inverse x, where this ft m inverse is the generalized heat kernel. And these are the references. And this Dengel, who is the whose work are mainly in this Dengel transform, Dengel operator. And in the second references, we can find the linear canonical Dengel transform. And this is the mean value property. And the third reference is mainly for the mean value property associated with the Dengel Laplacian. So thank you.
Thank you very much for your nice poster presentation and for your time. Does anyone have any questions? You can raise your hand, virtual hand, or write your question in the chat.
Okay, maybe I will share one question. Do you know if for this notion of transform, on Dong transform, are there some results about boundedness of convolution operators?
Yes, sir. In the normal setting, as if we take a one function from L1, the function should be L1 function should be radial, and the other function is in any LP. So the convolution product will be in LP, which is bounded by the one norm of the function and the p norm of the function. The same result, whatever things are available in Fourier, is also available in Dengel setting.
Like Young's inequality
Yeah, Young's
like
inequality.
Young's
Yes, sir.
inequality. Oh, wow. Thank
Yeah.
you. Thank you. Thank you. Very nice presentation. Thank you.
Thank you, sir.
Thank you very much. So we can continue with our program. Our last presenter of today is Daniela Lescano Cuello from Universidad of Córdoba, Montería, Colombia, presenting their poster titled The Hidden Secrets of Prime Numbers. Daniela, you here?
Hi, can you hear me?
Yes, now I can hear you. Yes. You can share your screen. Thank you.
Okay, hi, it's an honor to be here. Mi nombre es Daniela Lescano, soy de la Universidad de Córdoba, de Colombia. Una introducción muy general de lo que es el secreto de los números primos es que cuando estamos en el colegio, nuestro profesor nos dice siempre que es un número primo y sencillamente nos dice de que es un número que tiene dos divisores, el uno y el mismo. Pero desde antes, desde los antiguos egipcios, han estado estudiando cuál es el patrón de los números primos y aún no hemos descubierto absolutamente nada. Este póster va encaminado a hacer un estudio de lo que es la cogentura de los primos gemelos, que nos dice que entre un número primo y otro siempre va a haber un número par que los separa. Es decir, por ejemplo, el número 5 y 7. 5 y 7 están separados por un número par, que es el 6. Otro ejemplo sería el 17 y el 19, que estaría separado por el número 18. Entonces, si nos vamos a varias investigaciones utilizando herramientas de la teoría de números, eh, no tienen que ser ni siquiera avanzadas, sino que usando el principio de encasillamiento, podemos llegar a todas las conclusiones que han resuelto nuestros antepasados. Por ejemplo, suponiendo que la hipótesis de Riemann generalizada es cierta, Hardy y Littlewood en 1926 llegaron a este razonamiento. Sin embargo, lo suponieron en un intervalo. Y a medida iban como mejorando ese resultado. Es decir, primero este resultado con O, que es la notación de Landau, lo mejoraron y fue hasta 2013 que se hizo un resultado muy significativo, que es el de 70 millones. ¿Esto por qué es significativo? Porque ya tenemos como una estimación fija de dónde podemos acotar esos números primos que sí cumplen con la condición de la conjetura de los primos gemelos. Entonces, la misión que tienen algunos matemáticos ahora mismo es acotarlo hasta llegar a 2. Cuando se llega a 2, ya se da por terminado ese problema. Cuando Jitan Chan, que es chino, llegó a este resultado, lo que hizo fue que se creó una comunidad de matemáticos y también pueden, que no sean matemáticos, contribuir a la idea de cómo acotar ese resultado. Y luego en 2013, Maynard y Terence Tao acotaron un poquito más ese resultado a 600. Esto lo hicieron porque primero aquí el resultado más importante se enfoca en que es muy importante lo que hizo Jitan Chan. Eh, el propio Maynard, que es de Oxford, dijo que él hizo un montón de cálculos supremamente difícil para llegar a ese acotamiento. Y lo hizo siguiéndose del teorema de Bombier y Vinagre. Pero cuando Maynard y Terence Tao empezaron a como a acotarlo un poco más, ellos sencillamente lo que hacen es, en vez de seguir como las mismas ideas y mejorarlas, se van más atrás y cogen como otro camino. Entonces, y ese otro camino es ver el tamiz de Selberg unidimensional en uno multidimensional. Entonces, básicamente, básicamente lo que pasa es que esta investigación se basa en que no todos los caminos tienen que ser como correctos. Podemos mirar diferentes tipos de caminos. Y entonces, al momento de seleccionar los patrones, tenemos, por ejemplo, el patrón de los primeros n primos, que eso se puede analizar usando una herramienta en Google que se llama OASE. Y entonces lo que hicimos en la investigación fue tenemos el primer número primo. Entonces, ese primer número primo le sumamos el segundo. Y así, ya sabemos que los números primos son 2, 3, 5, 7, 11, 13. Y así. Entonces, nos va a dar una secuencia de números. Entonces, esa secuencia de números, vemos que también se siguen repitiendo otros números primos ahí. Aquí está está el 41 también. Y así. Entonces, queremos saber si en esa sucesión se puede aplicar también la coyuntura de los primos gemelos. Básicamente así se va la idea. Un- eh, para esta herramienta de internet es esta. Eso es, y uno aquí puede buscar la secuencia que uno quiera. Se han encontrado secuencias de que no tienen como un patrón y es sumamente chévere este tipo o sea, siento que es sumamente chévere este tipo de investigaciones porque es como tratar de buscar orden en el caos. Eh, Se le hace un agradecimiento al profesor Danilo Andrés García Hernández por el apoyo y todo lo que se hizo aquí se hizo siguiendo las ideas de lo que hizo Terence Tao en su revista que publicó en lo que publicó en Annals of Mathematics y lo que hizo Maynard, más que todo lo que hizo Maynard, porque él en su tesis de maestría, él hizo como una monografía de todo lo que había hecho de la coyuntura de los primos gemelos y eso sirvió bastante para resumirlo. Claramente no está traducido al español, pero siento que sería muy hermoso seguir este tipo de ideas, así sea que digan que la teoría de números es muy compleja. Entonces, eso quería compartirles hoy.
Thank you very much, Daniela Lescano. Gracias. Your talk was really nice. Me encantó tu charla. So now, does anyone have any questions? The talk was in Spanish. If someone has some questions.
No una pregunta, quizá una pregunta, pero después.
Okay.
Pero sí quiero agregar un comentario. ah, de pronto en inglés sería como, no mathematicians should allow themselves to forget that mathematics is a young man's game. O sea, los matemáticos no deberían olvidar que las matemáticas son un juego para los jóvenes, ¿no? Dice Hardy. Y me parece que esta charla es exactamente una representación de eso. O sea, Daniela nos ha mostrado con su pasión por la teoría de números realmente cómo se pueden gozar las matemáticas. Entonces, organizamos estos espacios, los organizaron Andrea y Karina para, digamos, inspirar a las mujeres matemáticas, pero finalmente somos nosotros quienes nos inspiramos al escuchar, digamos, la pasión, ¿no? Con la que los jóvenes hoy viven las matemáticas. Entonces, es muy impresionante esa pasión que muestras y que mostraron también los otros presentadores, ¿verdad? Yo solo quiero preguntarte, digamos, de las conjeturas en el campo que mostraste, ¿cuál conjetura te gustaría probar, demostrar?
Sí, siento que me encantaría hacer un aporte en la coyuntura de los primos gemelos, porque siento que se puede como ejemplificar como que son dos personas que por algún motivo no pueden estar juntos. Bueno, así podemos representar el 17 y el 19. Siempre están separados por un número par
Bien,
y sería como chévere.
imagínate,
Poético.
hace años
Sí,
atrás hubo un encabezado de Harald Helgoff, un matemático latinoamericano, que hizo un gran aporte, ¿no? A la teoría de números con la conjetura de golpe. Entonces, quizá en unos años una matemática de Córdoba pueda ser, ¿no? Un aporte tan significativo. Ya veremos. Y te animamos a que continúes con ese camino.
muchas gracias.
Daniela, yo tengo una pregunta. Hace un mes fue noticia en el mundo que encontraron un nuevo número primo. Yo no sé nada de teoría de números. Lejos, lejos, lejos de tener idea de teoría de números. Pero hace un mes más o menos leí que habían descubierto un nuevo número primo. ¿Tiene que ver algo con the twin prime number o algo así relacionado? No sé, solo curiosidad. porque es un 2 a un número súper extraño que encontraron y me causó curiosidad si tenía alguna relación.
Sí, sí, es que sabemos desde hace mucho, es más, es una demostración muy bonita por contradicción de que los números primos son infinitos. Sin embargo, cada día es muy difícil encontrar números primos. Por ejemplo, yo una vez escribí un código en Python para ver cuántos números me generaba y demoré como 4 horas esperando que compilara y aún los números eran como de 6 cifras. Entonces eran sumamente pequeños porque encontrarlos cada vez es muy difícil. Sin embargo, no sé cómo es la investigación para encontrar números primos. Hay gente que tengo entendido que se dedica solamente a eso y, o sea, y les pagan. Es como las investigaciones que uno hace. Entonces, tengo entendido de que ahorita mismo ese número llena como, o sea, no lo puedes escribir en un tablero completo. O sea, eso es un número supremamente grande y las calculadoras no pueden con un número tan grande. Entonces, no sé cómo, o sea, sinceramente no sé cómo hacen los matemáticos para encontrar esos números, pero cada día es muy difícil encontrar el siguiente número primo. Eso sí es un dato que hay que tener en cuenta.
Ok, gracias Daniela por tu hermosa presentación.
Solo a modo de comentario, quería, bueno, primero agradecerte por tu presentación, Daniela. Y también quería comentar que uno de los motivos por lo que los números primos son tan buscados o procurados es porque entre muchas funciones, ellos sirven para encriptar códigos. Entonces, entre más números primos encontremos, pues tenemos una gama más amplia para hacer ese trabajo. Y esa es una de las razones, pero existen muchas otras. Nada, solamente quería hacer ese comentario y agradecer nuevamente por tu nice exposition. Thank you very much.
Okay, so thank you all for joining us today. We look forward to seeing you tomorrow at 2 p.m. CET, Central European Time, for the second day of the conference. So have a great evening.
Bye bye. See you tomorrow.
Bye. See you.
See you tomorrow. Bye bye.